Okay, so let's get started with today's workshop. I'm really excited for this because I've planned for this workshop for quite some time, and this is the first time I'm actually conducting this live. So we have two sets of people who are in the participants today. One is who are already present in our live classes, and one who are just specifically attending this workshop. So I'm still admitting a few participants. Yeah, and regarding the lecture recordings, I'm recording today's lecture and tomorrow's lecture as well, and will be immediately sharing with all of you once the recording is done. So no need to worry about receiving the recording after the lecture. For the people enrolled in the live classes, I'll upload it to the dashboard as always, and for the others, I'll send you through email. So the reason I thought of conducting this workshop is because the way I have also thought about retrieval augmented generation or RAG has changed a lot over the last, I would say, last 2 years. There is a question, do we need to code along with you? Yeah, you definitely will need to code. So I would highly recommend not attending this workshop on phone because it's just not a good experience. We'll be coding everything from scratch. So if you attend on phone, then we'll be doing everything on Google Colab. So let me get started with the lecture objectives. And when I say lecture, we'll have two lectures actually within this workshop. I'll first tell you what all we will try to accomplish, and then we'll start going through each and every single thing in detail. So I'll tell you my RAG journey, right? So RAG stands for Retrieval Augmented Generation. No need to be scared by this name. The name itself looks a bit complex, like retrieval augmented generation. We'll see what all of these words actually mean. But before that, I'll tell you uh, my experience with RAG. So there are some questions in the chat. What do you mean by students attending live classes? So there is a live batch which is going on in the hands-on LLM series where we have, this is in the middle of our course. I will cover agentic RAG, but not in this workshop, in our subsequent lectures of the live classes when we reach agents. Okay, so if you take a look at RAG tutorials, you'll see that there are number of tutorials which pop up and which are small. So there are some tutorials which are 10 to 15 minutes in nature. There are some tutorials which are just 5 minutes. There are actually RAG tutorials which teach you how to build a chatbot in 5 minutes. Then there are these 20-minute tutorials, 25-minute tutorials. And when you watch these tutorials, you feel that, okay, this is simple. I've understood what is retrieval augmented generation. But it's actually not the case. Only when I started solving industrial problems, then I realized that the whole pipeline is actually far more complicated than what is shown in these introductory videos. There are several things which no one ever talks about, right? So for example, chunking. Chunking is very briefly mentioned in introductory videos, but no one codes through chunking and actually teaches engineers which chunks to use at what time. If you don't know these terminologies, don't worry, I'm going to cover every single aspect in detail. Then second is file parsing. In most of these tutorials, it's already assumed that you have the file. But in fact, that's one of the most important steps and frankly quite challenging. Then another aspect which is neglected is evaluation, which I'm calling as evals. And in industrial settings, evals has become critical because, okay, you build a rack pipeline and you submit it to the client or for your internal workflow, but is it working or not? How are you continuously monitoring whether your rack pipeline is delivering good results or not? And more importantly, there is the question of embeddings, right? In all of these short tutorials, they randomly use vector databases or vector stores without even thinking about why do we need to use vector stores? Can we just do embeddings in PyTorch? and what are vector stores. We are going to see all of these today. In fact, at several portions of this tutorial, I'm going to have this section called Engineer's Choice. This Engineer's Choice section I've specifically curated based on my own industrial experience. So unlike all of these tutorials, I don't want to tell you that go ahead and use this, go ahead and use that, but I'll be making you aware of the trade-offs. And when I say trade-offs, I mean how you should select the tool for your particular use case. So my goal after this workshop is that when you face these trade-offs in industry or wherever you want to implement it, you should be in a position to decide what's the best tool for me. I'm going to show you the different trade-offs which I encounter in our industrial problems. And then, so we are going to assemble a whole RAG pipeline from scratch. And when I say from scratch, we are not going to use a library like LangChain or LangGraph today or tomorrow, because all of that will seem very simple to you after going through this workshop. We are going to code everything from the ground up. And while doing that, we'll see what are the different engineering choices you need to make. While doing that, I'll also show you the different packages and libraries which are coming up, which are useful in industrial settings. So look at this workshop not as a toy series, but rather as an industrial level workshop where when you go to industry, things are not white and black, right? They are gray mostly. There is no right solution, but the engineer who stands out is the one who can figure out what's the best solution for the given problem. That's what I want to teach you. So if you have any questions at any aspect, right, ask me. My goal is for you to understand the nuts and bolts of this RAG in detail. So it should not just be a terminology which you think that RAG, okay, RAG is easy, I can cover it in 10 minutes. After this, all of you will be able to build chatbots, and hopefully you will be able to understand the trade-offs when we build pipelines. So what's our end goal? Our end goal after this workshop is that we want to build an application such as this, where if you see, this is a RAG-based nutritional chatbot, and it's built entirely from scratch. There are also two types of RAG systems, one who directly provide the answer, and one type of a system which, when it provides the answer, it also provides the citations. So we are also going to look at how to provide references, how to provide citations, and what does it mean when it says 56% match or 55% match. The front end, we will not spend too much time on the back end and front end coding. We are going to do it through Lovable. So all of us might get different looking websites at the end of this workshop, but that will be the fun of it, right? We'll share the websites which all of us have obtained. Yeah, and so the lecture will be such that I will explain many aspects through a whiteboard, and then there are several code files which I have designed. All of these code files I share with you at specific intervals within this workshop. All of them will be on Google Colab. Tomorrow, we are going to use tools. The only external tools we'll need is Supabase. How many of you have heard about Supabase, by the way, or used it before? It's fine if you have not heard of this tool. I'm going to show you what it is because it's used a lot in production level settings these days. Supabase is one tool we'll need, and second is Lovable. That's all. For everything else, I believe that even if you have the T4 GPU, which is provided for free through Google Colab, you will be able to follow along in this workshop. As the fundamentals, or as the, I should say, guiding principle of most of this lecture, the prompt engineering rules which we saw in some of our previous lectures are going to be important. So let me just introduce the 7 key elements of writing an effective prompt. First is, so the rule is called PICFATD, which is basically when writing a prompt, you have to define many things instead of just writing a quick prompt. The first is persona, then you have the identity, then you have the instruction, then you have context, then you have format, then you have the audience, the tone, and finally the data. These are the 7 key elements uh, of an ideal prompt, and we are going to use this in when designing RAG pipelines. In fact, the base of everything which is to follow, such as RAG, then later we'll look at agentic workshops, we'll look at MCP. The base of all of that is a good prompt. Uh, so please keep these 7 things in mind when writing an effective prompt. Don't just write something quick. And I'll stress that today when we are building this chatbot project also, it is extremely important that you spend time writing a prompt, because think about 5 years into the future, right? If English is going to be the new programming language, then prompt engineering suddenly becomes front and center. Then I'll take some questions in the chat, but before that, let me tell the philosophy of this workshop. The way I've designed this workshop is that it will cover all these 3 aspects. It will cover foundations, that's the most important, according to me, where you should know the nuts and bolts of the entire RAG pipeline, and you should be able to make engineering decisions when the time comes. Second is practicals. So at various places, I'm going to give you practical insights regarding which chunking strategy to use, which embedding strategy to use, how to deploy the RAG project. That comes in practicals. And then finally, I'm going to leave you with research questions or research directions. So after this workshop, I'm going to show you what are the open research problems in this area, which you can now immediately start working on after these live sessions are done. Let me take questions in the chat. So Prashant has asked, this might be a question for later, but should everyone move from plain vanilla RAG to agentic RAG? In production setup, we are only seeing 55% accuracy with standard RAG. That's a good question, Prashant. So I'll tell you my experience from industry, right? So far, we have done around 16 industrial projects. Out of those, 10 projects have been RAG-based projects. And in that, we have been able to satisfy the customer with a pure RAG pipeline. And when I say vanilla RAG, it's not just a simple, you upload a PDF, you query from that PDF and you give it to the LLM. In that pipeline which we designed for the customer, we did not use agents, but we used many modern things which grounds the responses. I'm going to share that knowledge also today. But vanilla RAG is working for problems which are not too complex, in my opinion. So let's say an industry comes, there are many chatbot requirements in industry. All of those can be solved with vanilla RAG. Then not just chatbot, there are some level 2 requirements, which is basically a company wants to make a code generator based on their docs. That can also be solved by RAG. Agentic RAG plays a very crucial role when you want access to external tools or when you want to do something complex. Let's say a company wants to build its own deep research agent. That is a difficult thing, and their traditional RAG won't play an important role. But at least in my experience over the last 1 year, the one of the main reasons I thought of taking this workshop is RAG is still very relevant, and vanilla RAG for many company problems of level 1 and level 2, let's say chatbot generation, code generation based on what they have, etc. Then another question in the chat is, when will the lecture notes and recordings be uploaded? So lecture notes and the recordings I'll share after each lecture is done. So after the first lecture, I'll share it on each participant's email, the link to the whiteboard notes and the link to the recording. Agentic RAG is about, agentic RAG is basically, I'll explain that to you, but in a RAG pipeline, you have access to embeddings, right? So think of embedding store as a tool. If you start thinking of embedding store as a tool, then it suddenly becomes an agentic pipeline where along with all the other tools, the agent also has access to the embedding store or the vector store. Would you discuss query transformations? Yes, I will discuss that towards the end of this workshop. Plain RAGs, would they help in application modernization like small ERP? Yeah, definitely. if you have, let's say, one common application which I would like to share with all of you is ITSM tools. How many of you are aware of this? What is ITSM? In information technology service management, right? So if you look at least India, there is a whole middle layer of companies which operate in the ITSM space, where they provide, let's say you are on Razorpay and you make a payment through Razorpay. What happens on their backend? How is the payment stored and processed? That's essentially information technology service management. If you are on Book My Show and if you book a movie ticket, what happens on Book My Show server? How are they managing different clients which are booking? That's usually managed through an ITSM company. So these companies usually provide dashboards to players like Zomato, Book My Show, players which need an IT infrastructure. Those dashboards are based on legacy systems or traditional pipelines for a very long time. And now they want to integrate chatbots within those dashboards. For these type of integrations, RAG systems will still play a very crucial and an important role because they usually have a fixed data size and data set. Llama index, yeah. So Llama index and LangChain, LangGraph, all of them can implement RAG pipelines very easily. And if I were to make a tutorial on Llama index using RAG, that will probably be a 25-30 minutes tutorial. But my main aim here is to build such a strong foundation that after this, any tool will seem very simple to you, whether it's Llama index, LangGraph, LangChain, anything. So let's get started now. So I've used this terminology RAG many times so far, right? And those of you who don't know or have not heard of this, do not worry about it. I'm going to motivate it in a lot of detail. So for the purpose of this workshop, we are going to consider, imagine that we are in the nutritional domain. So the document which we are going to consider is this 1200 page document on human nutrition. And I'm going to share uh, this drive link right now with all of you. We will see what these different things are. We don't need them right now. For now, all you can do is that when I'm showing this PDF to you, you can go ahead and download this PDF from this drive link, which I've just shared on the chat, so that you can also refer to this PDF along with me as I go along. Now, I want to ask all of you a question, right? Imagine that you are working in an industry, you are in the engineering team, and you are in a meeting with a client. The client has started a nutritional startup, right? And they want to spread awareness about nutrition globally, and for that they want to make a chatbot. Okay, and they want to make a chatbot which looks something like this. So essentially a customer will come, a customer will log in, and a customer will ask some questions, and the answer which will be generated has to be very specific and has to be very grounded. I'll use this term grounded a lot. What does grounded mean? Grounded with, whenever someone says grounded, you should ask grounded with respect to what? So this startup wants its answers grounded with respect to the encyclopedia of knowledge which it has, which is basically this book for now. It's a 1200 page PDF about human nutrition 2020 edition. And it talks about a huge number of things, starting from basic concepts in nutrition to human body. Then it goes to water and electrolytes, whatever. It covers every single thing about nutrition. They want their answers specifically coming from this book. Now, this same example I'm taking of human nutrition, you can translate it to other domains as well. If you want to make a chatbot for customer service, there would be a manual for customer questions and what should be the ideal answer. If you're making a chatbot for this ITSM, there will be a question, there will be a manual of tickets which customers usually raise and a sample of the solutions. Now, my question to all of you is that, let's say you are sitting in that meeting as an engineer, right? And this client comes to you with this request of making a chatbot. Forget about RAG or this terminology of retrieval augmented generation. Let's think from first principles. How will you build this chatbot? How exactly will you build this chatbot? So let's say that's the goal, right? The goal is to build a nutritional chatbot. But what's the key terminology which I mentioned? It should be grounded. It should be grounded in factual knowledge based on the book which I just shared with all of you. How will you do that? Add the document content somehow as a prompt. Use the PDF and pass it to the LLM. Okay, so what Madhusudan has mentioned, let's say you don't know all of this. That's the rack pipeline you are mentioning. I'm asking you to think from first principles, where forget all of your knowledge, let's say. The only thing which you have, let's say, is that you have a chat GPT, right? You have access to chat GPT or any LLM for that matter. Let's say you have this, and that's the only place where you start from. Add the PDF in the context of the LLM, instruct to answer information found in the PDF. We will load data to chat GPT. Okay, so the simplest thing which many people are saying and which is aligned to the data portion of this prompt, right? I showed you this 7 steps of the prompt, and there is this data portion over here, which is where we usually feed the data and which is where we usually ask the question. So many people are saying that, okay, this seems like a simple enough task. Why not I just use. There is also an answer from Prashant about keyword-based search. So keyword-based search, okay, that can be done. So, but you want to use a modern approach. So you propose to the client that, hey, this seems like an easy thing to do. We just make a front end. We just make a front end. And that front end looks something like this. This is the human query. This is the answer. This is the human query. This is the answer. So human query I am mentioning by HQ, and this is the answer, human query and HQ. So you start thinking from the front end, then you think that whenever the human query is asked, you pass it to an LLM directly. Whenever a human query is asked, you pass it to an LLM like ChatGPT, and along with this, you also pass the PDF directly. You pass the entire PDF. Then you make this API call to the LLM, and then you get an answer. That answer now you show in the front end. Then the user asks another query. You again make an API call to the LLM. You again pass the entire PDF in the context of the LLM and you get the answer. That's what would have naturally come to my mind if I were thinking from first principles and if I did not know anything about uh, retrieval augmented generation really. But what are the issues with this approach? Can you try to think that as an engineer, you go back and you try to implement this now? What will be the issues with this approach? So Amit is saying high cost, Samrat is saying too many tokens, context length, too many tokens. So let's actually see this, right? And I encourage all of you to do this in practice. Go to ChatGPT. I went to ChatGPT right now and I put this exact same PDF and I asked, what are the number of tokens in this document? What are the number of tokens in this document? Does it fit your context window? What is context window? Context window is the number of tokens which a language model can look at one time before producing an answer. So think of it something like imagine you are being bombarded with information. Let's say someone tells you about one topic, then the lecture goes on for 2 hours, 3 hours, 4 hours, 5 hours. At some point, you will start losing information, right? Context window is the maximum amount of information you can fit in at one time and produce coherent answers. Now, whenever an LLM like GPT is designed, the context window is fixed. Um, so if you ask something, if you put this document and if I ask what are the number of tokens in this document, does it fit your context window? So number of tokens seem to be around 400,000. And the context window of ChatGPT, and I'm using GPT-5 here, it's around 128K. So here we see that the entire document does not fit into memory at once. And what will happen if the entire document does not fit into memory? If you ask a question, let's say related to, if you ask a question, if the human asks a question related to this chapter, nutritional issues, and if in the context only tokens until page number 700 are going to be filled, then there is the entire context is lost. The LLM will not be able to answer correctly. Answers will be wrong. And then what will the LLM do? Do you know what the LLM will do after this point? The LLM might start to answer from its own knowledge of pre-trained information. The LLM says that this document does not fit in my context window and I don't see the relevant text in my context. So I'll use my own pre-training data. That's fine. I don't need to rely on any document. And when an LLM becomes overconfident like that and starts thinking like I have data from my own knowledge or my own corpus, that leads to one of the major problems which retrieval augmented generation actually solved. And that's the problem of hallucinations. Did not fully solve it, but was a good step in that direction. So if you pass the entire PDF at once, it might exceed the context window of language models, and that might lead to hallucinations. This is the problem. What is the solution to this problem? The solution to this problem came with this paper which was released in 2021. And the solution to this problem is retrieval augmented generation. Now, you can read through this paper definitely, but the idea of retrieval augmented generation is very similar to an example which you all know. Let's say you have also been given this text. You have been given this text on human nutrition, and you have an exam, but that's an open book exam. You have an open book exam. So let's say, I hope all of you know what an open book exam is, right? In an open book exam, you can put the book in front of you and you have access to all this material. So you have access to the entire book actually an open in an open book exam. So you are sitting in that lecture hall and you see a question. You see a question related to proteins, let's say. How will you answer this question at that point? Can all of you try to think about it? If you are sitting in that open book exam and you have been asked a question about proteins, what will you do? Yeah, go to index, find the topic and find it in chapters index. Yeah, so what all of you will probably do is that you will you will look at this word proteins, then you will go to this PDF from start. You will maybe look at the chapter of index or table of content. If it's not there in the table of content, you will go through all the pages and you will try to find that page where this particular information shows up. Then you will highlight that information, let's say. You will highlight that information. You will use this knowledge. So the question which might have been asked might not be completely related to this information, but you will use that information. And so this is the information coming from the book. And plus another key component which of course you need is your own mind. So your own mind already has some information, right? Because you might have studied for this exam. On top of that, you will get some information exactly based on this book contents, and then you will get the answer. Now, this entire pipeline is very similar to what a retrieval augmented generation is. Retrieval part is this part, the retrieval. And generation part is this part. So if you are not fetching context from this book, and if this whole thing was not there, so let's say I will move my screen now to this let's say if only this was there, that's just the generation part, right? But now you have augmented the generation part with some sort of retrieval from this document. That's where the term retrieval augmented generation actually uh, comes into picture. There is a question on the chat that do you plan to share your screen? Is my screen not visible? It's visible, right? Okay. So I guess it was frozen for some time. Whenever I go to this prompt engineering book, so let me close this book. Yeah, now I'm back to my main screen. So we retrieved context from this document and we also generated answer from our own mind. That's retrieval augmented generation. How does it translate in the case of the startup app which we discussed? The mind here, which I've mentioned, is the LLM with its own pre-trained knowledge. And instead of passing the entire context to the LLM, we only pass context which is relevant. And instead of using the word pass, a more fancy word is retrieve. We only retrieve context from that PDF which is relevant. So instead of this earlier pipeline which we saw, what if we make a different pipeline? What if the pipeline now is something like this? We still have our front end, and this is the human question, and this is the answer, right? So when the human asks a question, it will again go to the LLM, that is fine. But the LLM will also somehow magically get only that piece of context which is relevant. This is relevant context from PDF. And now that's the retrieval part. This relevant context is passed to the LLM and then we get the generation. Do you see the problem which this will solve? We started out with the context problem, right? Now we don't have to pass the entire PDF into the context. We only pass the relevant bits of information. What are the relevant bits? The same bits which as a student we highlighted over here when we were doing this open book exam. That's the relevant bit of information which is passed to the LLM. So the context window problem will be solved. The natural consequence of the context window problem being solved is that the LLM will now produce answers which are more factual. The LLM will now produce answers which are more grounded uh, in reality, based on the exact document which the client has given to me. Based on this exact document which the client has shared with me, my answers, now I can be sure that they will be specifically tailored. So when I ask some question here, and when you see the answer being printed on the screen, you will also see citations. Yeah, so these citations actually refer to what portion of the document this generation is referring to. See, this thing directly comes from the document itself on page number 592. This comes directly from the document on page number 53. So you are retrieving relevant pieces from the document from various places. It does not need to be from one place. You are passing it to the context of the LLM and then you are generating the answer. Okay, so that's the whole concept of RAG. So if you have any questions, please ask them in the chat right now. I'll be taking all the questions through the chat since the size of the room is quite large. This is the whole concept. So I just want to make sure ground, the stage is clear when we move to the next part. So one of the teaching philosophies which I follow is that before explaining anything, you need to understand the context behind it. So I know many of you might be wondering about the details here, right? Like how do we get the relevant context? Which LLM are we going to use? Are you using OpenAI API key? So let me LLMs, I'll come to that. That's again an engineer's choice. We can use an open source LLM and a closed source LLM. I'm going to do both. I'm going to use an open source LLM. So we are going to deploy a local RAG pipeline. And I'm going to use a closed source LLM also. Gemini Gems uses RAG. Yes. In fact, many of these players like Perplexity, they have a RAG pipeline underneath. There is a question by Sanket. What if the question is like summarizing the whole document? Wouldn't it have to parse the entire doc? Yeah, so for summary, there are multiple other things which we can do. For example, if you go to Gemini, right? And I also encourage all of you to try this. How many of you are aware of the context window increment in Gemini models? You must be aware of this, right? So actually what I did is along with ChatGPT, you pass the same document to Gemini. And what Gemini says is that this document does fall within my context window because apparently it has context window of the size of millions. Now, for Gemini, such a thing might actually work because the context window is very large. And there are many reasons why how Gemini has improved its context window. If any one of you is interested in that, I think the answer lies in this blog, uh, which is also a book, by the way. Yeah, just check this if anyone is interested in that. Anyways, that was a digression. There are multiple questions in the chat related to retrieval from multiple documents. So whatever I've shown you right now, right, it's just one document. You can retrieve from as many documents as you want. It does not need to be constricted to a single document. And then there is a question that where do we can we retrieve from a database or other format like images? We can. I'm going to come to that when I come to the ingestion pipeline, data ingestion pipeline. So Samir has asked, hallucination is due to large context. So hallucination can happen due to multiple things. In this case, there will definitely be hallucination because of large context, because the whole PDF will not fit in the context window. So the LLM will have to rely on its own pre-trained knowledge. So the answers which it generates won't be grounded to this document. That's why we call it as a hallucination. In case of RAG application, how important is the quality of LLM? Extremely important, in fact. But again, there is a trade-off here, Amit. What is the trade-off? The trade-off is with respect to what the organization values. If the organization values privacy, you want to have an open source LLM on your own server. We are in fact going to use an open source LLM on our local GPU. I will come to the trade-offs when we come to the engineer's choice section in that part. How important is quality? So this I already answered. Is the data, if the data is in tabular form? I'll come to data part just right now. So all of you who have questions about the data format, that's the next point which I'm coming to. Does RAG help in improving named entity recognition? 100% it does. And in fact, for named entity recognition, you have to do chunking in a very specific manner. We did an industrial project recently which had named entity recognition. For that, you will have to do chunking, which is called as structural chunking. We are going to cover that. Okay, so there are many questions which I will slowly start answering. Many of these questions will become clearer. But one thing which I do want to address is what was RAG in 2021 and what is RAG now? So in 2021, retrieval augmented generation was this cool new thing which had come to prevent hallucinations, and it's still relevant because it still solves industrial problems. But now just zoom out a bit and take a look at retrieval augmented generation in context of something which is called context engineering. So now there is this new field which is emerging, which is called context engineering. We talked about context a lot, right, in RAG, and already I mentioned that as the context window of LLMs is increasing, for example, what if the context window of all LLMs becomes 5 million? It might happen that in the next 2 years, RAG becomes irrelevant, right? Why? Because you can just pass the entire PDF to the LLM. Again, there is a trade-off. Like even in Gemini, I would not do this. Why I would not do this? Because Gemini charges you per token in the input and per token in the output. If you pass, let's say, 100 PDFs, even if the context window is large, you will incur that much prohibitive cost, right? So even if the context window of LLMs becomes large, RAG will still be valuable to reduce costs. Although LLM can handle it from a performance point of view, it's still not in your best interest to pass the full document. It's like using an elephant to kill an ant. Although you can do it, that does not mean you should do it. It will be costly for you. For every single request, why do you want to pass all the documents? You will get charged per token. But now think of RAG in the context in this within this umbrella of context engineering. In the last class, we have discussed prompt engineering, right? That's intimately connected with RAG. And one more thing which is intimately connected with both of this is memory. Essentially, if you are interacting with this chatbot which I showed to all of you, if I'm interacting with the chatbot, let's say a user logs out and comes the next day, how does the LLM know what conversation has happened yesterday? Imagine that I go to a nutritionist, right? I go to a nutritionist and I ask a question, or I ask multiple questions. I have a 1 hour session and I go back again the next day. The nutritionist will, of course, remember the thread of our previous conversation. Or the therapist, if you go to a therapist, they, of course, have to remember what has happened in the past. So when you talk about context engineering, memory becomes a very crucial role. Here also there is a trade-off. The more memory you save for an LLM, the more context it has, the more, again, the cost increases, the context size increases. But when you think about RAG, these days you have to think in terms of what's the context window of the LLM? Do I really need RAG? Okay, if the context window is large enough, like Gemini, I don't really need RAG, but I still can do it to save costs. Then how much costs can I save? Why have I mentioned prompt engineering here? Because the success of your RAG pipeline also depends on how good your prompt is really. Sanjeev is saying, can you explain context engineering? Yeah. So if you think about context engineering, the best way to explain context engineering is if you want to make a production level app like a RAG chatbot, how are you going to manage different aspects which show up in the context? What are the different aspects? One is, of course, the information retrieved from RAG. One is the memory. One is your current state. Then second, where are you going to save this context? Are you going to save it in a vector database or are you going to save it in a normal database like Postgres? Where are you going to save embeddings? I will come to most of these issues in this workshop, but context engineering is a much broader field now. And 2025, RAG has evolved now in 4 years. Now we think about RAG in terms of context engineering. The main field is context engineering. And then we start to think that, okay, with this context of the LLM, this is the application. What's the best thing which I can do? Should I do RAG? Should I just do few short prompting by passing the whole PDF? How am I going to save memory? Should I save all the conversations as it is, or should I save a summary of the conversations? Uh, think about this, right? If you talk with someone and if the conversation is for 1 hour, after 1 hour, what do you remember? You don't remember exactly what that person said, right? You remember the summary of key points which your mind automatically forms. So you can use another LLM to summarize. Anyways, I'm digressing a bit here. So it is best practices around context, yeah. And when you say context, it means many things. It means memory. It means the context window. It means the state. Will RAG be relevant in the long run? LLMs themselves, yeah. So this, I think I already answered, Amit. Let's say if you are JP Morgan, right? And if you want to make a chatbot specific to your data, I think RAG will still be relevant because passing the entire PDF each time will be computationally and cost-wise prohibitive. Okay, so let's table the questions for some time because now what we have to do is that we have to get started with the first pipeline. Many people have asked questions about document pre-processing and I want to spend some time here. This is the whole pipeline which we are going to build in this workshop, by the way. Let me walk you quickly through different elements. We are going to start with this nutritional PDF. Then we are going to do chunking. So this is the data ingestion part. I am going to have a section on this. Then we'll have a section on chunking. Then we have a whole section on embedding. Then we have a whole another section on LLMs, whether open source LLM or closed source LLMs. And then finally, we'll put all of this together and run everything on a local GPU. After this is done, we will do production level RAG and build this website. So we do have a number of things to cover. The pace at which we are going, I'm not really sure how much time this workshop is going to take. I'm very happy to answer all the questions, but from your side also, uh, please note that it may take more than 3 hours because we have to do all of these parts. So let's see. Actually, let's take a call based on how much we cover today and how much we are able to cover tomorrow. Okay, so the first step is data ingestion, right? And this is often the most neglected step in tutorials, in video sessions, everywhere, because it's not very cool. When I say cool, everyone talks about embeddings, LLMs, but the part which I think many should definitely be talking about is how are you going to collect the data and how are you going to store the data? So let me ask all of you, right? If you have this PDF, how will you collect this PDF so that a Python interpreter knows what to do with it? How will you open this PDF and how will you read this PDF in code? So we need to ingest the data somewhere. Our LLM is going to look at that data and then answer questions. But right now it's in PDF format. We humans can see it, right? But a Python code needs to understand it. So someone is saying PDF to text, pain of document parsing. Yeah, so this point, Prem, which you have mentioned, I'll come to that. Yeah, we will use a Python library basically to do document pre-processing. What document pre-processing is essentially downloading and reading PDFs. Now, in this section, I want to talk about three things. I want to talk about a document which only has text. Then I also want to talk about documents which have text plus images. And I also want to talk about documents which have text plus images plus tables. So if you have a simple document, right, which is in a PDF format, you can use packages to load the document. And one popular package is PyMuPDF. So I'm going to show you several packages and the way we decide for problems which one to use. So this workflow which I'm giving you right now is exactly what we do internally when a problem comes. So check this package. Actually, let me show the GitHub version of this package. So PyMuPDF is a traditional Python library for data extraction of PDF documents, really. Very robust library. What it does is that using this library, you can essentially pass in any PDF. You can pass in any PDF and then you can open the PDF using PyMuPDF. Using this library, you can also read different data. When I say read different data, you can read different pages. So for example, this entire PDF can be ingested by this library, and then we can save what information is there in every page. Now, let me ask you this question. Let's say this image comes. This image comes. What do you think this PDF extraction library will do at this point? So all text, skip it. So I'm looking for a specific answer. So first, let me ask whether it will be able to deal with this image or not. Actually, those who are answering no, that is not the correct answer. It will be able to deal with this image because this is a digital image. So there will be an image tag associated with this image, and this image will be downloaded as an image format. But the main issue is this fact. Let's say you get an image like, let's say there is a restaurant bill and someone takes a photo of this and uh, uploads somewhere. Let's say someone takes a photo of this and uploads. Will the library I'm showing with you deal with this type of an image? It will not read this type of an image, and that is one key thing to understand. I mean, it will save this entire thing as an image, but it will not read what is the text present on this image unless the text is typed through a digital form. If the bill is generated through a digital software and every field which is entered is a digital field, that will be taken into account by a tool like this. But if you have a image which has some characters, so what do you mean by digital? By digital, I mean if you let's say if you go to an invoice software, yeah, if I go to an invoice software tool, I fill entries over here and I generate PDF from this tool. That will be digital entry because every number is digitized. Then a standard PDF extractor can also read that number, can also see what is mentioned here. If it's digital, we can copy text from the PDF. But if it's not digital like this, we cannot copy text from this PDF, or at least normal Python libraries cannot. That is where we need libraries which can deal with something called OCR. So the best open source OCR library, you can also see from the number of stars which it has, is Tesseract. How many of you are aware of this? Tesseract is one of the most popular OCR libraries. But before introducing these libraries, all of you should know why OCR is needed in the first place. For the current PDF which we have, many of you gave the wrong answer here, right? We don't need OCR library here. This is just a simple image. There is no text on this image. A simple PDF extractor can deal with this image. You need to use OCR libraries only when you have images which have, let's say, handwritten text, images which have been scanned and uploaded into a document, which might be the case for many clients. So that is the place when you need Tesseract. So Tesseract can extract handwritten text, digitally scanned text, etc. Tesseract can extract text from images like this. That's the second option which I wanted to show you in this data ingestion pipeline. Let's see. How would the text extractor know if the image has text or not? It would not know, right? It would just, you mean the Tesseract? The Tesseract knows it because the libraries which it uses specifically looks for text in that image. But if you use PyMuPDF, it will not know. It will just save that entire image as one image. Oh, the fruit image, right? It will not know whether there is text or not. So even if this image has a text, PyMuPDF will save it as an image. But we will not know what's the text written on that image. That's the main issue. The image will be saved. That's not an issue. But all the information on that image will be accessed as a whole body. There will be nothing like there are characters in this image or there is text in this image. The granularity will be lost if you don't have an OCR tool. Then there is a question of tabular data, right? How do you deal with tabular data? For that, what I want to really do is introduce a third library, which has now become extremely popular. And I would say it's hands down one of the best libraries for uh, language modeling tasks. How many of you have heard of this Docling? Yeah, so Docling is relatively new. It's, I think, newer than all of the other libraries which I showed to you. But they have already, so we have used Docling in our industrial projects and it's amazing. One reason why Docling is amazing is because it is specifically meant for generative AI. What do I mean by that? So whenever Docling encounters a table in a PDF, the tables are saved as real tables. Rows and columns are preserved. Docling can even convert a schema into a JSON format directly. And if any one of you has used language models in production before, you know that it's very important for you to retain certain elements in JSON format or in Markdown format. So if you encounter a table somewhere, or if you encounter uh, any schematic or a schema, that can also be analyzed by Docling and that can be saved as a table. Further, Docling can be linked with an OCR tool as well. Docling can be externally linked with an OCR tool like Tesseract. So you have the OCR capability as well. You can extract tables very easily. You can extract schemas very easily. In fact, if any one of you is interested to read how Docling does it, this is the Docling technical report where they actually mention exactly how they manage to retain tables in an actual tabular format, etc. What happens if the input document has text, images, tables, and images with text, right? Then exactly what you will do in that case, if your text document is extremely messy and if it has images, if it has tables, if it has, um, let's say, images, scanned copies, then you can use Docling and you can use OCR along with it. If your document is very simple, like what I have, you can use PyMuPDF. If your document does not have too many tables but just has scanned images, you can use Tesseract. So this is the first engineer's choice section which I have. I mentioned at the start that I will have this section for all these parts, right? Data ingestion, chunking, embedding, and open source or closed source LLM. So this is the first point where I have this section called engineer's choice. When given a project, what document processing tool are you going to use? That's the first thing which you need to understand. And that depends on the type of documents which you really have. Now, actually, before this, there is one more step which I have not discussed, and that is related to scraping. So it may happen that some websites, if you go, or some client websites have PDF which you can download. But in some cases, the data is not in PDF format. So you need to first scrape that entire data and then use these processing tools which I've just mentioned to you right now. How can we have hybrid pipeline with all these three? So Samrat, if you want hybrid pipeline, right, then the best is to use Docling with an external OCR tool. If you go to Docling in the document itself, they say that they can handle diverse format. That's good. Um, they can export into various formats like Markdown, HTML, JSON, and most importantly, they have extensive OCR support for scanned PDF and images. So this one library has all of these things. If you are dealing with complex PDFs or if you are dealing with complex images rather. One more thing which we explored at Visuara recently is this Mistral OCR. How many of you are aware of this? They have a special language, they have a special model which they have released recently, which is apparently supposed to be very good at OCR. Uh, okay, so one good question has been asked in the chat that what about this Miro board itself if it's to be retrieved? Now, let me ask this question to all of you, right? Let's take this Miro board which I have. Which tool will you use to retrieve text from this board? Docling for sure will be good, but I would probably use Tesseract for this. The reason I would use Tesseract for this is actually What do I have here? If you think about it, I have some images and I have some text, right, which is written. And this text is very messy. So if you take images of this, of course, a normal PyMuPDF will not be able to handle this. But I don't have too many complex, like I don't have any table really. Even this table which I have, that's an image. This is not a real table. So technically, I don't have any tables. I would probably take images of this, make it into a PDF. So I just have PDF, I just have images, and I have text which will be scanned. So I definitely need an OCR tool over here. Yeah, this Mistral, right? I want to spend some more time on this because this is new. This has just come out. I think it came out 3 months back. Or yeah, we are trying it at Visuara right now. I don't know how it is, but it's supposed to be amazing. And there are several such LLMs itself which are specifically meant for doing OCR tasks. Scraping, right? So let me tell a bit about scraping right now. So let's say you go to Mahindra and Mahindra website and you are doing a project with Mahindra, and what they have told you is that I want to make a chatbot which is specific to Mahindra Rise, let's say, but they have not given you any data. Then what will you do at this stage? How do you collect the data if the client has not given you PDF copies of the data, or if the client has not given you like anything about the data? The only thing which you can do at this point is called as scraping. Yeah, so what you have to do is that you have to go through different sections and you have to use a scraping tool to scrape this data. I'm going to tell you 2 to 3 scraping tools which can be used. So first is called Firecrawl. Uh, Again, very good scraping tool. It has around 50,000 stars. One good thing is that it actually takes, with this Firecrawl tool, you probably don't even need a PDF extractor tool because it already takes the entire website and converts it into LLM ready markdown or structured data. That's one tool. Then second is, as someone has mentioned in the chat, Beautiful Soup. If you have HTML pages, especially Beautiful Soup looks at that and fully extracts that. And another thing is called Puppeteer. Uh, so it's an automation tool actually. With Puppeteer you can do some clever things. So someone mentioned about named entity recognition, right? So what if you want to go through different sections, but you only want to take headings or titles from each page? How will you do that? With a normal web scraper, it's bit difficult to do that specific amount of extracting. In Puppeteer, what you can do is you can automate the scraping by telling that I only want font size of this, or a header tags to be selected. I only want paragraph tags to be selected when you scrape. So that way, I think Puppeteer, you can also install this as a JavaScript library. Yeah, so it's an API to control Chrome or Firefox. It can go through. So my question to all of you is this: let's say if a client has 5,000 links, you cannot manually go and scrape each link, right? You need an automation tool which goes through this link, it scrapes whatever is there. Then it goes through this link, scrapes whatever is there. Puppeteer provides you that advantage. You can automate an entire workflow through Puppeteer and just sit back and get all the files downloaded. But you need to define that workflow very nicely. Selenium also. Selenium is good. But Jaideep, I found that Puppeteer, at least, so we had a client project where we used Puppeteer. They had around 5,000 documents they wanted to be extracted through scraping. And manual scraping took a long time. So we used Puppeteer at that moment. How effective is Firecrawl when dealing with websites? Yeah. Then it's not, I'm not sure actually how it bypasses the authentication. of websites. I need to check that. Yeah, manual scraping, right? It takes huge amount of time. In fact, for the client project which I mentioned earlier, we were doing manual scraping, but it was just too expensive in terms of time and everything. Is extracting data in tabular format? Yeah, definitely, Ashwini. So basically, the Docling tool which I mentioned, right? It can extract data from anywhere. It can extract data from images, tabular format. It can extract data from PDF snippets, basically anything which you want. But just keep in mind that if any of you is actually working on an industrial project, sometimes clients don't give you data even in PDF format. Then you have to do scraping on top of it. Okay, now what we are going to do is that we are going to code the first part which we just saw. I will take the remaining questions in the chat, but first what we will do is that for this PDF, all of us have identified that we will use PyMuPDF. Yes, did everyone understand why we are using PyMuPDF for the current task? Can you type yes in the chat if you have understood why we are using PyMuPDF for the current project and not any other tool? Okay, good. So now our coding journey is going to start. I'm going to share this Google Colab code file with all of you. And after the data extraction is done, we are going to take a small break. So I know attention time spans are a bit less, but no issues. So this is the Google Colab code file, and someone has asked to share the PDF, right? Yeah, so for the PDF, I actually shared this document at the start of the lecture itself. Not document, this drive folder at the start of the lecture itself. Oh yeah, so Jaideep, that's a great point which you mentioned, which I definitely want to address. I forgot to address actually. Uh, so you might be thinking, why does PyMuPDF actually exist, right? Because it's extremely fast. PyMuPDF is 10 to 15 times faster than Docling. That's the trade-off here. So if you go, there are some Reddit threads which actually argue about this. Yeah, see, Docling is at least 50 times slower than PyMuPDF. So if you have a simple text like what we do, don't use the powerful libraries unnecessarily. That will just be very slow for you. But that's a good point you bring up. I wanted to touch upon that, but it slipped my mind. Anyway, so all of you have access to this notebook now. The first thing which you have to do is you have to go to runtime and you have to switch to T4 GPU. We are going to start very slowly and we are going to start with the data ingestion pipeline. Okay. So before that, there is a long text here which you can even read after this lecture is done. I have covered this all in the initial portion of the class. This schematic also I have shared on the Miro board. Now what we can do is directly start from here, requirements and setup. So if all of you are connected to T4 GPU, this notebook should, by the way, by default already connect you to T4 and then just click on this. So the first two cells are where we are installing the packages. These two steps will take some amount of time. So I'm going to wait for here till all of you are running this. And meanwhile, let me answer some questions in the chat which I might not have seen. Can you share the PDF? I think I shared it right now. I am working on a project where I need to extract release documents from GitHub pages. Is Puppeteer a good choice? Yeah, definitely. First, Spursh, I would encourage you to explore Firecrawl because Puppeteer is a very low level library. When I say low level, it directly operates at JavaScript. So if you want to use Puppeteer, you need to be very comfortable with JS code. Firecrawl abstracts many things, so it's easier to use. If you are comfortable with JS, then I would suggest to go ahead with JS. Sure. After setting up the data pipeline, the biggest challenge I faced was keeping the changing data synced with the vector database. Any suggestion? Great point, Prashant. I will come to this. I do have a suggestion for this, and in one word, the suggestion is to use PG vector. uh, we are going to use PG vector. Essentially, the best thing to keep database versus vector database synced is to keep everything in one place. That's the only way to do this is to use a Postgres database with PG vector. I will see that tomorrow. Where can I get the link to this notebook? So link I have already shared. Oh, I shared the copy link. So in this copy file, I have removed the Hugging Face access token. Yeah, this is that link. There is some question in the chat about this book. This actually, I have not seen this yet. Let me check this. Yeah, it seems to be very highly cited, especially for vision-based document retrieval. One metric which I look for to check how popular a tool is GitHub stars and how active it is on GitHub. So it seems to be quite active. Last commit was made 5 days back. Um, that's a good paper. I'll definitely add it to my read list. It is asked to me in an interview if we extracted NER using LLM or RAG, how will we validate if they are correct? Again, a very good question. So, Prem, always remember that there are two types of validation, right? Uh, there is structural validation and there is semantic validation. When I say structural validation, it means whether the structure of your retrieved items are correct or not. And one way to implement structural validation, which we have already seen in one of the previous lectures, is to use Pydantic, where we can check whether the format is correct. But to do semantic validation, there are two types, either human as a judge or LLM as a judge. Where if you want to do semantic validation, either you have the ground truth data and you validate with that, or you use a larger LLM to give you the ground truth data and validate your extraction with that. How do you keep track of good papers and make it a habit? Yeah, so that is a bit challenging. So one thing which has honestly worked for me, Amit, bit counterintuitive, is LinkedIn. My LinkedIn feed is extremely well curated. And that is also because I spend a lot of time scrolling through LinkedIn. And I read, mostly I'm on LinkedIn. So I read things which I like. So algorithm picks up on that. So everything which I get is from people who talk about new things. Um, so I'm following some key set of people who, whenever something new is released, they will post it. So mostly I'm trying to avoid flashy things on LinkedIn. There are like two camps. One camp is like whenever, let's say context engineering, right? Whenever context engineering is a thing, then someone will make a post that 5 reasons why you should learn context engineering. I avoid those. But on my feed, there are people who write about, let's say, context engineering. What are the papers you should read? Then how is it different from? So more informative and not too much flash. It's getting a challenge for me, but I make it a point to at least read 2 papers per week and also implement those. I don't have a to. I do have a to read list. I'll share it with you. That's only that I make it week to week. I have it for this week. So on this week's to read list, I have this transfusion paper. This paper is on my to read list this week. Uh, and one more thing is on my to read list is the link which I already shared with you. It's this. In fact, I already ordered one of these books to our office because I am now encouraging all of our people to master GPU programming. I can't believe they made this free. It's the amazing but an extremely complex go through of how LLMs utilize our GPUs. But I like ordering physical books, so I've ordered 2 copies of this for our office. This is also on my to read list. I finished 2 chapters. I'm going to make a course on this because I have literally not found a single good course on GPU programming anywhere. Okay, so how many of you have finished running until these two steps at the moment? How many of you have finished installing packages? You have, right? Okay, good. Now what we have to do is that the next step is just document processing. So in this part, we are going to download the PDF. If it does not exist, it's fine. So one way is to just add it on the left hand side over here. But if it does not exist, in this code, we'll just go ahead and download the PDF. And the next code block is where we are actually going to read this PDF. So let's go through this code block step by step. First, there is a text formatter. So what it will do is that it will make sure there are not empty spaces in any of the text which we are reading. Then we have this open and read PDF. So this import fits which we are doing, right? That's the PyMuPDF. This PyMuPDF GitHub repository, when we do import fits, that loads the package. And the way we open a file through PyMuPDF is doing fits.open. Then what we are going to do is that we are going to go through every single page in my document. I'm going to get text from that page. So page.get text. Okay. Then what I'm going to do is that I'm going to format this text to remove empty spaces. And then what I'm going to do, I'm going to maintain a list. So I'm going to maintain a list like this. So every page, for each page, I'm going to store the page number, the number of characters on that page, the word count on that page, the number of sentences on that page, and the actual text. Okay. So what this piece of code is doing is that we are maintaining a list called pages and text, and each element of that list is a dictionary. So the first element of this list is page 1. First element of this list is page 1. And what will page 1 have? Page 1 is a dictionary which contains all of these. Similarly, the second element of this is page 2, etc. So what I'm essentially doing is that I'm making a list, and in each list, this is page number 1, this is page number 2, dot, 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 right up till page number 1208. And in each page list, I'm storing these values. I'm storing the page number, I'm storing the text. Of course, the main thing is the text also I'm storing. So you can run this now. And then what you can do is that you can just randomly print out 2 dictionaries from this list. So I have printed out the page number text for one page, and this is for second page. So you might be wondering, why is this minus 41 here, right? Why am I subtracting minus 41 over here? The reason is that if you actually take a look at our book, right, it really starts from page number 41 or 42 here. This is where our book actually starts. Yeah, here. So what is actually page number 1 is page number. So you need to subtract 42 pages actually to get to page number 1. So all of the pages which come before this are marked as negative since we subtract 41, and then page number 1 will rightly start from here. And then what we can do is that we can just get a random sample. So now our dictionary or our list is called pages and text, right? That is our list. We can get a random element from this list. So we can see we have got page number 1019. The number of characters are 1574. Number of words are 270. Oh, by the way, we are also maintaining number of tokens. So for this, the simple thing we are doing is number of characters divided by 4. That's the number of tokens which we are assuming. So each page dictionary will look something like this. We have page number, the number of characters on that page, the number of words on that page, the number of sentences on that page, the actual text, That's it. And then what you can do is that you can actually get some statistics on the text. So just run this and get the different statistics. So for example, for this page, the character count is 29, the word count is 4, the sentence count is 1, the page token count is 7.25. And then you can get an overall statistics. So this is the main thing which we want to focus on right now. Mean. Let's take a look at this mean row. So on an average, all pages have roughly around 198 words. On an average, all pages have around 10 words, 10 sentences roughly. And on an average, each page has around 287 words. Why is this important? Why are we looking at the number of tokens on each page? Can someone try to think? Why are we looking at the number of tokens on each page? There is an error which Krishna has got, pages and text is not defined. Krishna, have you run this? Because we have defined pages and text over here. Now I'm going to the whiteboard, and the question which I'm asking to all of you is that we got these statistics, right? We got these statistics that each page has, let's say, yeah. So eventually we want to take, so let's say we want to take a page and we want to convert the page into an embedding vector. To do this, let's say we use this, let's say we use this model, all MP-NET base V2. The issue is that in very fine print, they have mentioned that input text longer than 384 word pieces is truncated. So that is going to be an issue for us. If our page is more than 384 or 400 words, we cannot embed our entire page into a vector using this model, because then some information will unfortunately be lost. So that's why it's just a better idea to make sure that whenever you're looking at pages, just take a look at, okay, how many words do they have on an average? How many tokens do they have on average? So here it seems that each page on an average has 287 tokens, which is lesser than 384, right? So it is fine to go ahead with this. So potentially each page can be embedded with embedding models. Currently, we have not decided which embedding model to use. We have not even decided if one page is equal to one chunk. But potentially, if we decide that one page is one chunk and we want to embed each page, we can very safely use this all MP-NET base version 2. That's the reason why we should actually keep a track of how many tokens are there on each page, how many words are there on each page. The thing is, when you directly use RAG libraries on LangChain, all of this information is lost to you. They directly give you a PDF, but you should yourself see how many pages are there, what's the token count on each page, what's the word count on each page, what's the sentence count on each page, etc. We are going to come to chunking right now, so don't worry about it. The next thing which we are going to do is chunking. Rahul has asked a question, is RAG plus SLM a practical combination? Yeah, definitely. Because RAGs are much better than fine tuning anyways. We'll come to that actually after the lecture is done. That is mean. What about max? Sure, max, but check the standard deviation also, right? Standard deviation is 140. So even with this, it seems the one or two standard deviations are around, let's say, 400 token length or something. So we are fine. Sorry, I did not understand what you mean about LangChain. So when you see tutorials of RAG on LangChain, Llama Index, these tutorials are 10 to 15-minute long and they completely skip this part. They already assume that you have a PDF and then everything starts like at a much later stage. But in practice, this is what you have to do first. So this is the exploratory data analysis equivalent. when we do a normal machine learning problem, we do EDA, right? You also need to do some EDA when you do RAG. There is a question about lecture recording. So I will share the lecture recording, and the Google Colab, I've already shared it on chat. Okay, so now we are going to take a break for some time and we are going to cover chunking. I definitely do want to cover chunking today because it is one of the most important pieces of the puzzle, and nowhere on the internet, on any YouTube video, I have found comprehensive explanations of chunking. In fact, there are blogs on chunking, there are good blogs, but blogs can only take you so far, right? In the chunking section, what I'm going to do is that first we are going to understand all the types of chunking in detail, and then we are actually going to code different chunking strategies. We are going to code them from scratch, and we are going to compare these different chunking strategies with each other. But we will take a break. So earlier, what I had planned is that I had planned 1.5 hour for today and 1.5 hour for tomorrow. But I think today itself we will take around 2.5 hours. It looks like. So if any of you, I did not plan 3 hour workshop today, Sanjeev, honestly, but it's good that you are asking so many questions. We have many more things left to cover. So it depends on your time schedule. If all of you want to catch the recording, you can do that. But anyways, I will come back now after 5 minutes to start the chunking part. If you are available, you can stay live to watch the chunking. If not, I am going to upload the lecture recording anyways. Uh, yeah, Samrat, when we do chunking, it's not we don't need the EDA really later when we do the chunking, but it's still good to see what's the number of tokens we have. It might change our intuition later. Okay, so I'll just come back after 4 to 5 minutes. It might take 1 to 1.5 more hours today because so what we can do today, we can finish chunking, and then tomorrow we can do embedding the LLM and then the final production. Yeah, thanks guys. I'll come back after around maybe 9:35.
All right, everyone. So let's begin with the next part of today's lecture, which is going to be chunking. There is a reason why I have allocated a separate section to this, because I believe it is one of the most important pieces of the RAG pipeline. Let me explain to all of you why chunking is important. So until now, what we have seen is that we have processed the PDF. So we have processed the PDF. That part is done. Okay. Now, what we have to do is this is our LLM. The LLM will get a prompt from the user, of course, but the LLM will also get some retrieved information. The retrieved information from our knowledge base or from the PDF. Now, what we are doing in the chunking section is that we are essentially bridging this gap. We are essentially bridging the gap. So now we have processed the PDF. How do we go from this PDF to retrieving bits of information which are important? And there are two key steps to this. The first is chunking, and the second is called as embedding. We are going to look at embedding tomorrow, but today let's cover chunking. So the way it works is that if, let's say, let me take a sample. I've taken a sample screenshot of my PDF. The first thing which I'm going to do is that I'm going to divide this PDF into chunks. And when I say chunk, a chunk can be, let's say these are my chunks. This can be one type of chunking. So imagine that in the whole PDF, every sentence is one chunk. Or you can even have chunking, which is page level chunking. So this entire page is one chunk. This entire page is another chunk, etc. Now, let's say you do some sort of chunking and you have these chunks. You have 2000 chunks. Let's say you have split the documents, you have split the knowledge base or the document which you have into 2000 chunks. In the retrieved information, the only portion which you are going to select is some of these chunks. Maybe you select the chunks which are most closely related to the prompt, the top chunk. So you can select this one chunk, or you might select top 3 chunks which are most closely related to the prompt. So you can select one chunk, you can select 2 chunks, you can select 3 chunks. That you have to decide. But if normally people select between 1 to 10 chunks, so let's say you select 3 chunks, these are the 3 chunks which will be passed as the retrieved information. Now you see the problem here is that, or I should not call problem, the quality of your output is going to completely and solely depend on your retrieved information. And your retrieved information is going to completely depend on what type of chunks you have. Because if you have granular chunking like sentences, this will be just one sentence, this will be second sentence, and this will be third sentence. So you will just pass 3 sentences. But if you have broad level chunking like pages, then each chunk will be one page. So you will be passing page 1, you will be passing page 2, and you will be passing page 3. So imagine this as the brain of the LLM. And so this is the LLM and this is the data. The retrieved information which passes through the LLM will be from a list of chunks, and only a subset of these chunks will be passed to the LLM. So from the engineer's perspective, it becomes extremely important to decide how are we exactly going to do the chunking. There are so many ways, right? The sky is completely open that we can do anything. So now let me ask all of you, let's say this is the PDF. 1208 pages PDF. How should we go about chunking? What will you have as individual chunks? Heading wise. So Samrat is saying heading wise, right? So essentially, I think what Samrat is saying that wherever there are headings, you make that as one chunk. So make this as one chunk. So if carbohydrates is a heading, make carbohydrate section as one chunk. If lipids is a heading, make this section as one chunk. If proteins is a heading, make this section as one chunk. I think that's what Dishant means by sections. Aditya has an interesting suggestion. What Aditya is saying is that let me not focus on the structure of the PDF. I will actually write down all of your suggestions over here. So the first suggestion is based on the structure, right? So if we do based on headings, what else? Then the suggestion by Aditya is with respect to similar topics or semantics. Then Jaideep is saying document structure. So here let me bucket this in this segment itself and let me call this as a document structure at the moment. If they are big divided into paragraph, limited amount of word size has to be the same. Maximum number of tokens LLM can handle. So let me do the third category as fixed. So when I say fixed, maybe it's 10 sentences as one token, or 10 words as one token, or one word as one token. Whatever, this is fixed size chunking. So intuitively, if this terminology of chunking was not known to me, or if I had not studied the literature of retrieval augmented generation, I would have intuitively said that one chunk is one section. Because when I read a piece of PDF, my mind thinks in terms of sections, right? So if a certain question is asked by the user, ideally you should retrieve a full section and give it as the answer, right? I don't want to just retrieve few sentences. I want to retrieve entire sections and pass it. That's why I think chunking should be done section wise. That can be one example. There are people who are mentioning recursive for plus overlap. For some people, this might not be clear, so I'll come to that eventually. Okay, so that's the intuition which comes to my mind. Now, what we can do is that let's go through the 5 types of chunking which we are going to see. And then towards the end, we will also have an engineer's choice section on which chunking strategy to use. And then we will code the different chunking strategies and actually see their similarities and differences. So my hope is that after this section, all of you should understand the trade-offs. So at the start of the lecture, I mentioned about trade-offs, right? There are a lot of trade-offs in different chunking strategies. There is no one size fits all approach. And different chunking strategies definitely lead to different results. In fact, what we have done here is that we have actually made a PDF. I'm trying to find that PDF right now. Just a minute. Yeah. So within our company, we have made this PDF of chunking strategies. I'll share this with all of you, where this guide is especially meant for what are the different type of chunking strategies and which chunking strategy to use at what time. This is one of the most important things to understand for engineers especially. And my main purpose with this workshop is how to make engineering decisions like these. But to make engineering decisions like this, first we have to understand what are the different chunking strategies, right? So let's start now. Before even evaluating between different chunking strategies or coding, all of you need to understand what is exactly done. Some chunking strategies are easy to understand, some are slightly more detailed, but each of them serve a specific purpose. So first, let's go with fixed size chunking. So in fixed size chunking, what is actually done is that let's actually take a PDF. let's take this legal services agreement. Let's say you are making a rack system for a legal domain, right? And if you have a PDF which looks like this, where there is responsibilities of law firm and client, whatever. In fixed chunking strategies, what you mention is that I will have every chunk to be of a fixed size. So let's say my chunk one is of, let's say 200 words. So all my chunks are going to be 200 words. I'm not going to look at anything else. My chunk one is going to be 200 words. My chunk two is going to be 200 words. That's it. And I can also have a slight overlap between these chunks so as to make sure that some amount of context is retained. But can you tell me what's the drawback with this approach? What's the advantages and what's the disadvantages with this approach, according to you? So now here again, try to think from first principles, right? Imagine you're making this rack system where you want to make a chatbot where a customer asks something about an agreement and your chatbot should answer. Now the retrieved information will come in chunks. Why or why not should you go ahead with a fixed chunking strategy like this, with each chunk being of 200 words? Incomplete responses, context not covered, sentence cut in between, lacks contextual overlap. So yeah, let's take a look at this example itself, right, where it is being cut. So responsibilities of law firm and client. This should ideally be one full section, right? And I want this entire thing to be passed into my retrieved information. But because of this chunking, what has happened is that, let's say this chunk has responsibilities of law firm and client, right? So when a user asks on a chatbot, what are the responsibilities of a law firm and client? If this is the user asks this chunk will be retrieved. But this chunk actually does not have anything related to, it has some amount of context because we are retaining some overlap, but most of it is related to some other sections. So this chunk will not be retrieved, which means that we are actually losing out on this much amount of information, which is completely relevant to our current section. That's one major disadvantage with fixed size chunking. Chunks can be made in the middle of important paragraphs. Chunks can be made in the middle of sentences. So good question is asked, won't embeddings create a match for similar text? Embeddings will create a match, but what if your chunk is formed at a place where there is nothing with respect to the question which is asked? Let's say if it's just two sentences at the end of a paragraph where the context of what comes before is lost. If your chunk unluckily comes at that point where in that particular section the information of the title is lost, then that paragraph won't be retrieved. And currently I'm just showing a small paragraph, right? If you have a huge paragraph related to a section and if you randomly make a chunk halfway, some of your information can be lost in the retrieved chunks. Can the chunks be linked? So the chunks cannot be linked because let's say we have chunks. When you say chunks linked, that leads to structural chunking actually, which will come later. In fixed size chunking, this is the main issue. So then why would anyone do fixed size chunking? Can you think of an application where people do fixed size chunking? Why is this method even being discussed? So one lesson which all of us learned at the moment is that if your document has a structure like sections, subsections, etc., never go with fixed size chunking because it might cut a section halfway. Fixed size chunking is used in places where you want fast processing. Let's say if you have millions and billions of documents, right? Or hundreds of thousands of documents. And if you want a quick strategy without too much overhead, if you want the speed of processing to be quick, then you go ahead with a fixed size chunking because it will just be very fast. Like if you are collecting information from Reddit, if you are collecting information from Twitter, mostly the information will be disorganized in threads, in comments, no clear structure, no clear subheading, random messy information, but huge amount of information. If you have random messy chaotic information, which is huge in number, and if you want to process it quickly, you can use chunking. You can use fixed size chunking with some overlap. Now, these are the advantages and disadvantages of fixed size chunking. Quick, fast processing is the advantage. The disadvantage is that it has semantic breaks and the context is lost. So the strategy is best used in scenarios where documents are large and numerous, and a quick segmentation is needed without requiring deep understanding of the context. For instance, if you are processing millions of web pages for indexing and can tolerate some loss of coherence in chunks, fixed size chunking is a viable approach. Now remember that as the size of your chunk increases, your embedding model size also needs to increase proportionately. So keep that in mind. That's a trade-off with larger chunks. One other use may be in streaming or sequential processing. Yeah, correct. As it's easy to handle streams of text without worrying about sentence breaks. Agreed. Another use is book like Fountainhead. Yeah, sure. If you have books or let's say if I go to and if I take any book here, yeah, take a look at this book, right? It's a huge book which has no structure, it has no headings, no subheadings, nothing. Such kind of text, it might be good idea to maybe go ahead with fixed size chunking. And if you have 1,000 such books, then definitely go ahead with fixed size chunking. So let's say if you're doing a project on Project Gutenberg, and your task is to transcribe all the books, let's say, and come up with some sort of a rack system, it might be better to go ahead with fixed size chunking. Okay, that's the first strategy. The second strategy is what someone already mentioned in the chat. Now, again, here I'm taking the same example which I showed you over here. Now, let's say you take a book from here, the same book which we saw. The main issue again with fixed size chunking is that although it's fast, it does not retain anything about semantics, right? It does not retain anything about meaning. There is no meaning between one chunk or another chunk. Semantic chunking tries to solve this issue. So the way semantic chunking works is that first you have to define a level of organization. So by level of organization, I mean whether it's at a sentence level. So if I want a sentence level organization, what I will do is that I will take the first sentence, right? So let's say you have chunk number 1, and that's like a box. I will take my first sentence, I will add it to the box. Okay. Then what I will do is that I will take my second sentence. I will compare the embedding of this sentence and this sentence. So I will, so let's say if this is sentence 1 and sentence 2. So sentence 1 will be converted into a vector embedding. Sentence 2 will be converted into a vector embedding. And I will check if the similarity score between these two vector embeddings is greater than a threshold, let's say 0.8. If it's greater than this threshold, I know that both of these sentences are kind of meaning the same. So then I will add this second sentence also over here because it passes my similarity criteria. Then what I will do is that I will again go to the third sentence. I will embed the third sentence into a vector and I will compare its cosine similarity with sentence number 1. If it again passes the threshold, I will add it to my chunk. I will keep on doing this until I have sentences which have good cosine similarity with my original sentence. And the moment I encounter a sentence which does not pass this criteria, the moment I encounter a sentence whose cosine similarity is less than this threshold, I will stop this chunk. So that's my chunk 1, it's done. Then I move to chunk number 2. What this will ensure is that every chunk will have semantically similar information. So let's say when I go to this, let's say I want the initial section is all about a drama happening between a family. I want to have this chunk until that drama finishes. So whenever certain question is asked, I will only retrieve the chunk whose semantic meaning is matching. That's where semantic chunking actually has an advantage over fixed size chunking. It takes into account the meaning. So I know that every chunk will have similarity in meaning. Amit is asking what is chunking strategy used in Notebook LM. Notebook LM definitely uses, I think, chunking which takes semantics into account. So maybe something similar to the semantic chunking which we are looking at right now. If the sentences have high similarity, isn't it better to avoid them? So good question. But you will never be sure that why the similarity is high, right? So you might lose information that way. Instead, two sentences can mean something similar, but they are in different contexts. You can still have them. So let's say if you're talking about forests, you can be talking about trees in the forest, or you can be talking about taking a trip to the forest. And their semantics, maybe the vector embeddings are matching. So you won't want to neglect one compared to the other, right? So semantic chunking main advantage is, of course, it maintains coherence, and it is used in settings where integrity of ideas is very important. So for example, let's say if you have let's say if you are listening to a parliament debate, let's say you are listening to a parliament debate and you have collected the transcripts, right? You want to make a RAG system related to uh, you ask a question and then you want to identify what was discussed in this parliamentary debate. Now, usually, I don't know if you have seen, but parliamentary debates are some of the most unstructured and they can get chaotic, they can get messy. And but there is a flow of ideas. There is a flow of ideas in these debates. Someone talks something, someone else negates it. Usually, we don't know till what time that negation proceeds, or let's say we don't have a clear split, but ideas are there, and clearly ideas belong in buckets. For such kind of transcript rack system, I would go ahead with semantic chunking because I would want to preserve the integrity of an idea till the time it is discussed in one chunk. This is very similar to educational transcripts. Let's say if you watch a video and if you make a transcript out of this, right? So let's say this same video, let's say you watch this video and I talk about 4 to 5 things in the video, but let's say I have not added timestamps and I have not added anything. How will you know the key things which are discussed in the video? The only way for you to know is maintain the semantic integrity of chunks, right? You cannot do fixed size chunking here. You have to maintain semantic similarity. So then you will know, okay, this section talks about byte pair encoding. This section talks about the size of language models. This section talks about emergent properties, etc. Otherwise, there is no way to know from transcripts. So there are a number of cases when maintaining the semantic similarity in one chunk plays to our advantage. And again, the drawback, of course, there is no free lunch. There is no free lunch, and that's why the main drawback is that this kind of a strategy is extremely complex and it takes a lot of computational power because you have to convert every single sentence into an embedding, right? So that's not easy. Again, major issue is you have a hyperparameter here, which is the threshold. You have a hyperparameter here also, the number of tokens in a chunk, but here you have the threshold and you have no clue what this threshold sensitivity should be. At least this hyperparameter, you kind of have an idea that 200 words means this much. But here it's completely vague. Another thing is inconsistent chunk sizes. So some chunk sizes might be very huge. That might be an issue for our LLM context, etc. Let me see if there are any questions in the chat. You took one sentence at a time and then I lost how semantics is maintained. Do you scan the entire document? Yeah. So basically the way it is done, Samrat, is that it's done sentence wise. So you take this sentence number one, okay? You are doing sentence by sentence. So you take the sentence number one, you add it to a chunk. You keep on adding subsequent sentences to the same chunk until their cosine similarity with the first chunk, with the first sentence is above a certain value. The moment you encounter a sentence whose cosine similarity is not higher than the threshold, right from that moment you start forming the second chunk. Then you form the third chunk. Like that, you sequentially go through your entire text and keep on forming chunks. Does semantic chunking require pre-computing embeddings? Is it done at runtime? There are both options actually. Nowadays, actually, people have started using runtime querying. So you can do that during runtime, but most RAG applications I have seen, they maintain embeddings. What happens if the idea in chunk one and again come up somewhere after? That's a great question, actually. Yeah, then unfortunately that needs to be a separate chunk. But if the idea is close to the first idea, and if you're retrieving 4 or 5 chunks, hopefully both those chunks show up, right? Let's say if you make a chunk which has certain idea and that idea comes later at the end of the document. If both ideas are very similar, both those chunks will be retrieved at the end. Wouldn't it be a better strategy to check cosines? It will be, I agree. But the whole idea is that, again, the time also increases, right? If you want to check the semantic similarity with all the previous sentences, uh, it's a bit time consuming. Also, you kind of hope that the cosine similarity formula is such that if you take dot product of two vectors, A dot B is higher and B dot C. So if you think in terms of angle, if A dot B is higher, they are similar. If B dot C is higher, B and C are also having similar angles. So you can say that A and C will also be somewhat similar to each other. Is it based on assumption that next line will be similar to semantical similar to? Yeah, that is also true. That is the same thing which was exploited in what's the word to it? Neighbors usually carry similar meaning, right? Because you would not have random lines usually subsequently added next to each other. Samrat has said, so should we have structure? Yeah, correct. This level of organization which you mentioned, that can also be at a paragraph level in semantic chunking. If your sentences are not varying too much in meaning, you can have one big paragraph as one chunk. But then again, you will have to do structural chunking followed by semantic chunking, which is done. I'll come to that later. So that naturally brings us to actually, first let me cover structural chunking. Structural chunking, according to me, is the most intuitive form of chunking. And this can be combined with semantic chunking also. Structural chunking is essentially like, let's say you are considering a shareholder letter, right? So if you see, yeah, if you take a look at the shareholder letter and they are going to release it quarterly with the same kind of sections, structural chunking takes advantage of that approach where it says that we are going to split the report exactly at these section boundaries. The first chunk is going to be letter to shareholders. The second chunk is going to be introduction. The third chunk is going to be company overview. The fourth chunk is going to be financial statements. The fifth chunk is going to be notes to the financial statements. Sixth chunk is going to be conclusion and outlook. That's it. It's extremely simple, right? And believe it or not, in industrial problems, structural chunking solves many issues because it depends. If you are in a financial sector or if you're in a medical sector and if you're looking at a very specific RAG application, it is very likely that the application stays the same across multiple documents. For example, if you're building a conversational therapist RAG chatbot, the therapist might be making notes after each session in a specific format. So the therapist might be writing introduction or the key things which we discussed in the session, key takeaways. So as long as you know the structure of your documents, structural chunking is the most intuitive and the best thing you can do when you receive any problem. If the problem is a bit more structured, if it's messy, like what we have seen here, then of course it will not work. But if, let's say, if you have hospital records, or if you have stock price information in a specific tabular format or in a specific structure format, you can always leverage that structure. The more you leverage structures in a documents, the more grounded your retrieval augmented generation system is going to be, hands down, at all times. So the first strategy, which I always intuitively also it comes naturally to me, is just go to structure level chunks, right? Uh, but then what are the issues of structural chunking? Can you think of any issues with structure based chunking? In fact, many of you, when you saw this document, the first thing which intuitively came to mind is structure based on sections and subsections. That's exactly structural based chunking. What are the issues with this? Yeah, the issue with this is that the uh, one chunk can usually be very large. Because what if in one particular shareholder letter, the introduction section is 5 times longer than others? Then the chunk size becomes very large. Then that chunk will be retrieved to the language model, right? And will be added to its context. So then the context window of the language model becomes again very large. So the same problem which we set out to solve, we are again encountering the same issue again. So the advantage of a structured approach is that it's very good for documents whose data comes in structured format like section, subsection, etc. But it's actually not very good in terms of the fact that it can make chunks which are huge, and that might increase the context length of LLMs, and that might again lead to more hallucinations. How many of you actually know what metadata is? Uh, can you, so why have I mentioned metadata over here in structure-based thinking, in structure-based chunking? Yeah, so data about data is metadata, right? Essentially, if I know that a chunk belongs to a particular structure, so let's say when I store a particular chunk, I also store its metadata. That if I store an introduction chunk, I also store that it's an introduction chunk. I might refer to it later. So later, if I want to collect all the introductions, I might refer to this metadata also. So structure-based chunking also has this added advantage that since you know which chunk corresponds to which structure, for example, you know that this chunk corresponds to company overview, you can store that as a metadata, and then you can access that metadata later downstream in your application if there is a need. Now Samrat had also mentioned that can we in semantic chunking, instead of having sentence as chunks, or instead of level of organization at the sentence level, can we have the level of organization at a paragraph level? So one paragraph will be added, then the semantic similarity with other paragraph will be compared. So if you want to do that approach, you are essentially combining structural chunking with semantic chunking. Because first you will use structural chunking to find the paragraphs. Then you will use semantic chunking on top of that. So that's a combined approach. And normally, if one type of chunking fails, it's very common to combine two types of chunking methods also. So this disadvantage of structural chunking, which we saw, the main disadvantage is that some chunks can be too large. That is solved by recursive chunking. Recursive chunking is an amazing chunking strategy because it's kind of the best of both worlds. It exploits the structure. So it exploits the structure of documents, but it also kind of makes sure that chunk size remains consistent. How does it do it? So let's take a practical example actually. Yeah, let's take a look at, let's say you are building a RAG chatbot which analyzes research papers. Now you know that if you are analyzing research papers belonging to a particular journal, the structure is going to remain the same, right? If I'm looking at patterns, they don't accept papers if the structure is too different. So I know that this is going to have some kind of an introduction section for sure. It's going to have a summary section. It's going to have a result section. It's going to have finally the conclusion and discussion section. Yeah. And then towards the end, there will be references and then it will end. You know, this is the structure. But in some papers, the result section can be too long compared to other papers. So you cannot use structural chunking. Simple thing is to just use structural chunking, right? And each section can be one chunk. So what recursive chunking does is that first I will make chunks based on my sections, right? So introduction section will be one chunk, result section will be one chunk, etc. Then I will look at my chunk size and I will define a maximum chunk size. If the maximum chunk size is 500 tokens. If one of my chunks is greater than the maximum chunk size, I will chunk it again. How will I chunk it again? I'll have to define one more level of chunking. So if the result section becomes too big, I'll say that I'll chunk it at the paragraph level. So then I'll again chunk based on paragraphs in the result section. So then each of these paragraphs will then become a separate chunk. And then what I do is that then I again go to the paragraph level and then I see whether each token is greater than a particular token is greater than my maximum size. And if some paragraph like this is greater than the maximum size, I will chunk it further to another level, which is my sentence level. And then I will again check whether the number of tokens are greater or not. So if you think about it, it's like that kind of Russian doll approach, right? Where you take a large level chunking, where you take section level chunking. Then within that, you have paragraph level chunking. So you do paragraph level chunking only when chunk size is greater than the maximum chunk size. So you do paragraph level chunking. Then in paragraph level chunking, again, if the chunk size is higher, you do your final level of chunking, which is your sentence level of chunking. So here again, you check whether the chunk size is greater than the maximum. So since we are using different level of chunkings, one below each other, this method is also called as recursive chunking. And the reason recursive chunking is the best of both worlds is because it's preserving structure for sure, but it's also making sure that none of my chunks are too large. So that won't affect my context size at all. Let's see. What if we combine structural with semantic? So this we already discussed. Is it possible to apply chunking strategies to images and videos in multi-modal models? David, that's a great question actually. It is definitely possible to do that. So think of images and videos in terms of tokens, right? Just like I'm talking about tokens for text, images and videos also have tokens. They have different token schemes. But the tokens will be different. The tokens will be at an image level. So there you have to use, again, you can use similar strategies, but the strategies are a bit more different than what we are currently covering. Can you define chunk size? Yeah. So basically, one hyperparameter we have to define here is that I will define a maximum chunk size myself. Before I do recursive chunking, I have to define a maximum chunk size. Let's say that's going to be 500 tokens. So at every stage, I'm going to compare whether my chunks are greater than this size or not. So if I do section level chunking, each section chunk, I will check its number of tokens. If it's greater than 500, I'll do the second level of recursive chunking, which is paragraph. Then again, if it's greater than 500, I'll do sentence level of chunking. How is this different from fixed size chunking? So it's completely different than fixed size chunking, right? Because in fixed size chunking, nowhere we are thinking about the structure. In fixed size chunking, I will just start randomly from my start, and I will, if my fixed size is 50 tokens, I will take this 50, that will be my one chunk. I'll take this 50, that will be my second chunk. I'll take this 50, that will be my third chunk. Here, what we are doing is that we are doing structural chunking first. So first, we break it down into sections. If each section does not have too many characters or tokens, then our chunking will be at the section level. Only if one section is larger than a token size, we will break it down further. Did everyone understand how this is different from fixed size chunking? Recursive chunking is actually completely different than fixed size chunking. There is no similarity at all between recursive chunking and fixed size chunking. Because in recursive chunking, we are not mentioning the size which we want. We are just mentioning the maximum chunk size. There is a question, how is the link saved in this chunk? It's not. In structural based chunking and recursive chunking, the semantic notion is not maintained here at all. Are there libraries to do? Yes, definitely there are libraries. Both LangChain and LangGraph provide libraries to do recursive and structural chunking. But today we are going to implement these from scratch in Google Colab. We are going to implement all of these chunking strategies from scratch. So Amit, it is not actually maintaining semantics because nowhere does it know what is mentioned in the section or subsection or paragraph or sentence. So to those people who ask the question about fixed size versus recursive chunking, is it clear how it is different? I think Sanket asked and Krishna also asked. If that is your main question, it means there is some conceptual gap. If there is no link, I might well as look at the, but there is a, the section is maintained, right? So you understand the benefits of structural chunking. The sections are maintained. So think of recursive chunking as a superset of structural chunking, which means that if you understand the benefits of structural chunking, by default, you already understand the benefits of recursive chunking. Because it is structural chunking, but it is a bit more clever because it ensures that each chunk is not greater than a particular size. Yeah, maintaining section somehow preserves. Yeah, that way that's correct. If you maintain a section, it kind of preserves what we are talking about. You can think of it that way then, Sanket. So in fixed chunking, so let's again go back to this example, right? Of the this example. This example would never happen in recursive chunking because in recursive chunking we would have defined that this whole thing should be a one chunk, let's say. It's just constrained by the maximum chunk size, and the maximum chunk size I can define it to be slightly larger so that on an average it takes into account all sections and subsections as one chunk. Is recursive chunking clear to everyone? Out of all the chunking methods, this, yeah, it is structural chunking on steroids if you think about it. That's clear, right? The last chunking strategy which to explore is LLM based chunking. And this is that strategy where humans kind of gave up, I think, because we are like, let me tell you what happens in LLM chunking. Take a look at this conversation. This is a transcript from about a user who is interacting with a chatbot about this car. So it's this car actually. So Mahindra's car, and the user is kind of interacting with a bot. The context is that the user wants to book a test drive. But the issue is that first the user asks about booking a test drive for this car. Okay. Then the user asks to compare prices and compare the value for money between the two brands. Then the user says that let's go with the test drive for 3XO. Then the user again switches to petrol or diesel option. Then the user again switches to where could you share your specific location? So user gives his location. So basically what I want to point out here is that this is a example of a conversation which is called as context drift. Because in one piece of conversation, we are talking about first a test drive, then we are talking about price comparison, then we are talking about feature comparison, then we are talking about location for the test drive, then we are talking about petrol or diesel. In one single conversation, there are multiple context drifts which are happening. So if I ask a RAG chatbot, what happened in this conversation? What did the user actually talk about? Then you kind of need a system so that a chunk maintains context across drift also. So you need a system where definitely you need semantics to be maintained here. You need semantics to be maintained, and there is again no structure in this conversation. So you cannot, three options are ruled out for you. You cannot do structural chunking, you cannot do recursive chunking, and you cannot do fixed size chunking. You can do semantic chunking for sure. But even in semantic chunking, sometimes it might get difficult to analyze the entire flow of the conversation, notice where the drift is happening, etc. So then the only way to do this is to bring an LLM into the picture. And then you ask the LLM that start looking at this entire context and give me those points at which drift is happening and then break those points into chunks. So you give that in the prompt itself. So nothing is defined a priori. You tell the LLM that this is the entire context which I have. Go through this entire context and break it down into chunks. How to break it down into chunks? Identify those points at which there is a context drift which is happening, and then do the chunking yourself. So the reason I said humans gave up at this point is because here we do not really take structure into account. We do not even specify too many things to constrain ourselves. We just tell LLM that you have to do this, let's say. So the advantage, of course, is high semantic accuracy and good for documents with rapid context changes or unstructured text, really. So if you are handling voice conversations as a chatbot where a person can ask multiple different things where context is drifting a lot, you need to maintain semantic accuracy across long sentences where LLM-based chunking can play a useful role. Disadvantage, of course, computationally expensive, context window limitations, because what if the LLM determines the whole context is important? That can again lead to context window limitations. And the moment we have an LLM, the output can be stochastic. So if you pass this chatbot to a client for the same question, you may get different outputs. Since an LLM is determining at what point you want to split into different chunks. Okay, so yeah, Sanjeev, you pointed an issue with LLM context window, which I covered over here in the disadvantages. If we are trying to retrieve similar content about a topic from archive or newspaper article, so then you can even, so that's the RAG system, right? Basically, what Anita, you're saying is you want to build a RAG system from an archive of newspaper articles. Newspaper articles, they might not be organized into structures or subsections, right? So the best way to get started with is either fixed size chunking or semantic chunking. Or if you can do OCR and you can make sections based on fonts. So one trick which I'm going to share with you is that if you take a look at this newspaper article, right, you definitely need an OCR tool. But how would that OCR tool know whether there are sections or subsections? One way to tell the OCR tool is that this is a business review newspaper, and usually they have this font. So wherever this font is there, make it as a section. Wherever slightly smaller font is there, make it as a subsection, etc. We are going to see that today because if you take our document itself, it's very difficult for our PDF tool to know where there are sections and subsections. So we are going to do a small trick when we code, where we are going to identify where sections and subsections are there. So if you can do this trick on your newspaper articles, and if you can figure out sections and subsections, you can do structural RAG. If you cannot figure that out, you can do fixed size chunking as a start. If it does not work, you can do semantic chunking. What do you mean by stochastic output? So by stochastic output, I mean, since you're using an LLM, by default, it's a probabilistic model, right? So if you use one LLM and again try to use it the next day, you might maybe, or use a different LLM, you get a different answer. So by default, the stochasticity is embedded whenever you use an LLM. Jaydeep is asking, there might be a relationship between embedding size and chunk size. Yeah, sure. So that's a trade-off, right? Currently we are discussing the trade-offs based on structure versus no structure, semantics, no semantics. Another trade-off is that also when we discuss structural chunking disadvantage, we said that potentially two coarse chunks that might affect the context window of LLMs. Another issue is that if you have chunks which are too large, you will need to use larger embedding models, because if certain chunk is too large, you cannot, let's say, use this sentence all MP net base V2, since the input text is only 384 pieces. Yeah, so that's the main issue. So for larger, we have to use VLLM, 1K token size, and for paragraph, maybe BERT. Yeah, sure. VLM, though if you use Peter, it's always going to be extremely computationally expensive. You can simply, without using VLM, if an OCR tool can be used, that might be faster. Many people have asked question about stochastic output. When I said stochastic output, I just meant since it's an LLM, and every time you interact with an LLM, the output can be different. How about documents which are related to each other? What chunking strategy would you use? So good question. Uh, if the documents, if the documents are related to each other, right, then hopefully the chunks will also be related to each other. And then when you retrieve the chunks, you can just retrieve more chunks, so that chunks from multiple documents are retrieved. Embedding model like Gecko embedding has fixed size dimension 768. How do we choose embedding model? We are going to come to that. So there is a separate section which I have on embedding, and we have a engineering choice section there also, but that will come tomorrow. Today, what we have to do is focus on chunking right now. So let me come to an engineer's choice section over here. And let me share with all of you which chunking strategy to use at what time. Okay. So the 5 things which we discussed, right? The main thing is that if you have data which is inorganized and messy, and huge amount of data which has no real structure, no real shape, go ahead with fixed size chunking and see if things are working. It's usually the simplest and the fastest method. Then if you're working with a client like medical sector, educational sector, healthcare sector who maintain records, if records are maintained, usually there will be some sort of a structure to the records. So you have to by default start with structure-based chunking. If you do structure-based chunking and if you see that some chunks are too large, then you will have to split it recursively using recursive chunking. Now, if you see that if you are transcribing, if you are using transcripts from a debate or from an educational video, you want to make a RAG chatbot based on, let's say, the build LLM from scratch playlist, but I have not added timestamps over there. You will still need to make chunks where semantic integrity is maintained between ideas. That's when you have to use semantic chunking. And if everything fails, if the context which you are analyzing has sharp twists and turns, if there is drift in the user interactions, then you should do LLM chunking, but this is extremely expensive. So usually no one does it for large documents. You can do it for a smaller collection of documents. All of these things which which I'm mentioning right now, right? I have actually collected all of those in this chunking strategies guidebook, which I shared with all of you. Actually, let me add this in the drive folder right now. I have shared this drive folder at the beginning of today's class. So I have added this PDF over here. This PDF, yeah, this PDF, right? So if you double click on this PDF, you will see this 20-page PDF, which contains all the different types of chunking which we have discussed. And it also contains a very detailed section of which chunking strategy to use at what point. Some of the examples which I have shown here are actually some examples in industries which we have implemented. And towards the end, I have an additional section which is, I have not studied these techniques in too much detail, but someone asked a question about multimodal aware chunking, right? This is a topic of active research right now. Another topic of active research is something called query directed chunking or dynamic chunking, where chunking is done on the fly. So instead of doing chunking before, and so the RAG pipeline we are discussing is sequential, right? Chunking, embedding, retrieval. Instead of doing chunking like in a predefined way, you can do chunking on the fly. So whenever a question is asked, you form a chunk at that time itself. That's called query directed chunking. So if anyone wants to get into chunking related research, these are some very good topics. Multimodal aware chunking is one topic. Query directed chunking is another topic. There was a section which I have actually, which we can go through quickly. And this will again make sure that the questions are clear. So if you, so these are some class questions to check which chunking strategy to use. Let's say if you're in a legal domain, you're building a system to answer questions about a country's laws. And laws are divided into articles and sections. If you're building a chatbot, what chunking strategy will you use over here? Yeah, so those of you who are answering structural or recursive, that's the correct answer. So I would actually go ahead with structural first. If it leads to larger chunks, I would go ahead with recursive. I would encourage everyone to answer on chat because this will test your understanding, your knowledge. Second is a financial domain. So if you have an earnings call transcription and want to do Q&A on them, where it might not have clear headings for each question, then what will you do in this stage? Where you just have the transcripts of the calls and you want to have a Q&A chatbot. Yeah, so the correct answer here is I would actually go ahead with a fixed chunking initially to see how it is working because it's fast. And if it produces answers which are not coherent, I would go ahead with semantic chunking. So the correct answer to the first question is structural and recursive. The correct answer to the second question is semantic. What about the third? You are processing patient electronic health records, where there are fields like chief complaint, history of present illness, lab results, assessment and plan, etc. Which chunking strategy you would go ahead with in this case? Exactly. So all of you are now getting the correct answer. Here you will definitely go ahead with a structural. And the last example I have is again from this build LLM from, let's say if you have this playlist and if you want to have a set of lecture transcripts, which you want to make it into a chatbot based system, how will you do this? Semantic. Or if semantic does not work, maybe LLM based chunking. Good. So now I hope that chunking strategies are clear for everyone. What are chunking strategies? Why we should use each chunking strategy? And the best way to evaluate a chunking strategy is, of course, based on the responses, right? It is not so only after the whole pipeline is done, you will be able to evaluate a chunking strategy. In fact, this code file which I have shared with you, this LLM production RAG main code file, I have two other code files which are related to semantic chunking and which are related to structural chunking. So what I have done is that in the current code file, which we'll start exploring again from tomorrow, we are going to use fixed size chunking. But I have run this exact same code file using semantic chunking as well as structural chunking. And then when you reach the end of both of these, you can clearly compare the differences between which chunking to use in your system. So even when you have decided the chunking strategy, only after you have run the whole RAG pipeline, you will be in a situation to compare which strategy is the best. But you have to go through the full RAG pipeline. So it's similar to tuning itself. You can think of it as a hyperparameter, and you should have some RAG evaluation framework and just check the metric in your framework. So then later you can have a graph between RAG evaluation, RAG eval frameworks and your chunking strategy. So chunking strategy number 1, chunking strategy number 2, chunking strategy number 3. So it might happen that on one evaluation, some chunking strategy might be working better. On other framework, on other evaluation metrics, some other chunking strategy would do better, etc. That's the way you decide what chunking strategy to deploy in practice. Ablation study and intuition, I would say, because I'm going to now take you through a code where you can actually visualize the chunks. And before doing the rest of the RAG pipeline, you can visualize the chunks, you can check their size, you can check the variance in the sizes. And then you can try to get to an intuition of whether this will work for your RAG application or not. That intuition is important to develop, which I'm going to show you right now when we are going to look through code. So in the code, which I'll share with all of you right now, what we are going to do is that all these evaluation strategies which we have seen right now, we are going to evaluate these strategies. And when I say evaluate, we are going to look at the different chunks which are being formed, the sizes of the chunks. We are going to look at the size variance in the chunks. This can be one evaluation which you can do before even running the entire RAG pipeline. So what all you have learned so far in theory, we are now going to put it in practice. We are going to put it in practice when we are going to run this chunking strategies notebook. So I'm just going to share it with all of you. Just take a look at this code. Again, here, before going through the code, I'm going to take a break of around 2 to 3 minutes. And then this will be the last section which we will cover today. Tomorrow, we are going to look at embeddings and assembling the whole pipeline and the remaining aspects. But today, until this point, it's going to be the last thing. So we are already at 2.5 hours into the workshop. I don't know how much more time this will take, but I will try to finish it in the next 30 minutes or so. So let me stop for some time and I'll come back maybe in 3 to 4 minutes at 10:40 or 10:41 a.m. IST. Thanks guys. For those of you who have still here, it's great that you are continuing to follow. We only have around 30 to 35 more minutes to go. After that, we'll see the rest in tomorrow's lecture. So I'll come back in some time. Okay, so now let us continue with the last part of today's lecture. There is a question on the chat related to how do we decide the chunk size if we are going ahead with the combination of structural plus recursive for legal framework. So that is going to be based on the document itself. So the way I would do it is that, let's say if you look at a document uh, and you try to kind of form a vague notion of what is the average section size or what's the median value of the section size length, and you can use that as the maximum chunk size. So this will make sure that at least major sections which are not big enough are retained into one chunk. And then the sections which are outlier in terms of their length can be in separate chunks. Okay, so I hope all of you have access to this. Let's start running the first code cell and let's start running the second code cell also. In this, what we are doing here is that until step number 2, we have already seen in the previous code, right? We are just loading the document over here. And we are collecting this list of multiple dictionaries, and each dictionary will be corresponding to a page number, the character count on that page, the word count on that page, sentence count on that page, and token count. This will again take some time to run, but we are on T4 GPU at the moment. How many of you have finished running step number 0, step number 1, and step number 2? Can you mention in the chat? Done, right? Okay, so I am running this a bit late, so it is taking a bit of time for me. But meanwhile, let's go through step number 3 now. This is the main step. What we are doing here is that we are testing 5 chunking strategies on our data set. What is our data set? Our data set is this, which is around a 1200 page PDF. And we are testing out different chunking strategies on this data. The first chunking strategy is where we are going to have 500 characters in one chunk. That's it. That's fixed size chunking, right? So a simple thing to do here is that you just go through all the words in a page and you keep on adding the words until they hit this fixed size. And once you become greater than that size, then you stop that chunk. So this is the simplest one to actually explain and also to execute. Basically, you just you pass the text of a page into this chunk text function. And this chunk text function, what it does is that it just looks at that text and keeps on forming groups of 500 characters into each chunk. So you can run this right now. So you can see that the total chunks are 3321, where each chunk is of 500 characters in our current PDF. Now what I wanted to do after this point is I actually want to visualize what every chunk looks like. So I've written a simple function over here which just prints out the chunk and what it looks like. So you can run this and you will see the chunks actually look like this. In this function, I'm getting five chunks which are randomly scattered throughout the data set. So take a look at the number of characters in this chunk. You will see that in some places there are character numbers 290. Can someone tell me why this is happening? It should ideally be 500, right? Why are the number of characters here 290? The reason this is happening is because we are looking at every page separately. So maybe we form one chunk, we form the second chunk, and the last chunk only has this much. That's why it might happen that some chunks would have lower number of characters than other chunks. But if you take a look at these 5 chunks, you will see that mostly their chunk size, the character size will be around 490 to 500. And this is how every chunk will look like. So now, when I told you at the start of the lecture that something will be retrieved If you remember at the start, we saw that something will be retrieved and passed to the LLM, right? This retrieved context, this relevant context, I called it relevant context over here. This relevant context will be retrieved and passed to the LLM. That is these chunks. Each chunk is a relevant context. So when I say relevant context, it will be these chunks which are passed to the LLM. And now along with the prompt, the LLM will also have access to these chunks. So it's similar to in an open book exam. If you are doing this open book test and you think something is important, you will maybe highlight this and you will utilize this information for answering, right? So this highlighting a piece of text while solving that open book exam is exactly similar to these chunks which I've shown over here. Where we have defined that we are looking page wise, the place where we have defined it is over here. So see here, the way it is happening is that we are first extracting the text only for a certain page. So the for loop goes over pages. We are looking at one page and one page text we are passing to this chunk text function. So it will form chunks for that one page. Then we go to the next page. Likewise. Okay, so this is the first method of chunking. The second method of chunking which we are going to see is semantic chunking. So here you will need to install the sentence transformers package. And the sentence transformer which we are going to use here is all mini LM L6V2. So let me show you. This is the one which we are going to use. And yeah, you can see the number of downloads for this. It's around 90 million, I think, 90 million downloads per month. It's a very popular sentence transformer model. We are going to, so remember in semantic chunking, what we saw is that in semantic chunking, you are going to take every sentence, you are going to convert it into a vector, and you are going to keep on adding the remaining sentences until the cosine similarity becomes greater than a certain threshold. Where is my file? Yeah. So this is my sentence transformer. And in semantic chunking, what we are doing is that we are ultimately going to call the same function. We are going to look at every page and we are going to call this semantic chunk text for every page. And in this semantic chunk text, what we are going to do is that we are going to first break that page into sentences. For that, we are going to use the sent tokenize function from the NLTK library. And then we are going to keep on appending the sentences to the current chunk until the similarity score is greater than the similarity threshold. If the similarity score is not greater, then we break out of this loop basically. I hope all of you understand this logic in the code. It's exactly similar to what we had discussed over here. You essentially maintain the new chunk and you keep on adding new sentences to that until the similarity score becomes greater. There is a question regarding how to know which model to use. We are going to see tomorrow how to use embedding models, but as a baseline rule of thumb, if you are new to this field, all mini LM L6V2, which I will also share in the chat, this embedding model, and also the MPNet V2, the previous embedding model which we saw, MPNet base, not the base one, the V2, this is the one which are good starting points. How about semantics chunking option from LangChain? So as Samrat, you have noted, many frameworks give semantic chunking options, which are exactly similar to what I'm showing right now. The reason I'm showing it from scratch is because then you will find all those approaches extremely simple and easy to work with. But under the hood, they are doing the same thing what we are doing over here. So you can run this right now. And what this will do is that this will actually need to download. So this line which I'm saying right now, I'm going through it a bit quickly, but you should appreciate the power of the open source community over here. Because if all of these models were not made open source, and if all of these models were not uploaded on Hugging Face, it would have been very difficult for us to utilize these models as simply, right? So this looks like just one sentence, but don't take this lightly. A whole revolution has happened, open source revolution, before we have come to this stage where we can very openly use Hugging Face and run these code files in Google Colab. So I'm using a similarity threshold of 0.75 over here. You can feel free to use uh, a different similarity threshold as well. So here you can see we are now doing semantic chunking for every page. Oh, I think my audio was cut off for some reason. Yeah, okay. Now here we can see that the total number of semantic chunks which are formed are 12016. Now, can you already see one thing? Why do you think the number of chunks in this case are so much larger than the number of chunks which we saw in page size chunking? Can you try to think why the number of chunks in this case are so large in number? Yeah, the reason is because it really does not make sense to use semantic chunking on our document. First of all, there is chapters are small, and then chapters are not that related to each other. Even within a chapter, there might be concepts, cover different concepts in different paragraphs. So the semantic notion changes very quickly. That's why very small chunks are becoming individual chunks, which is an issue here. So you can actually print out. So if you print out the chunks in semantic chunking, you will see the wide variance, right? In some chunk is this just this much. Some chunk has around 200 characters. Some chunk has 78 characters. That's one disadvantage of semantic chunking. Again, there is diversity in the chunk size, uh, but semantic notion between or within a chunk is actually maintained. So in semantic chunking, we got around 12,000 total chunks. Why is there no continuity of text in these chunks? So I have just randomly printed out not the entire chunk, but in some cases, the reason there is no continuity is after this sentence, there might be something new which might be starting completely, right? Maybe it's not related to the previous sentence at all. Let's just actually check this sentence now in the document. So this is that sentence, I think, observing the connection between beverage and longevity. Dr. Mechikanov began his research on beneficial, this sentence, right? Now, the thing is the sentence transformer model. If you pass this sentence and if you pass this sentence, according to the sentence transformer model, the semantic similarity between this sentence and this sentence is less than 0.75. So if you want to have longer chunks, one thing which you can do is actually reduce the threshold score over here. You can reduce the threshold score to 0.6. You can reduce the threshold score to 0.55 also. But I hope all of you can start seeing that what are we doing exactly here, and we are relying on this sentence transformer model, right? So the semantic threshold, semantic score might be lesser than the threshold. That's why it's not characterized into one chunk. Now let me come to the third section, which is recursive chunking. So the reason this collab code file has become long is because later when you refer to it, I have also mentioned detailed examples over here. So if you forget what was covered in the Miro board notes, even if you have access to this code file, it will be easy for you to revise everything in one notebook. So if you're going for an interview or something later, just look at one notebook, run it. And for chunking strategies which are a bit difficult to understand, such as recursive chunking, I've deliberately added this text section over here. Now, the reason the way we are going to do recursive chunking is something very simple over here. First, as I mentioned, we have to define a maximum chunk size, right, which is equal to 1000. Which is this Google Colab notebook? So the Google Colab notebook, you mean the access to this notebook, or I did not understand the question. How do we access the Miro notebook? Oh, this notebook, I've shared this notebook link with everyone on the chat. Oh, this notebook, this is the same as the one which I shared with you on chunking strategies. So this copy of chunking strategies and what I'm doing right now is the same, except that the API keys are removed in this. Miro notes I will be sharing with all registered people. I'll just share the link to this Miro note. So the way we are doing recursive chunking over here is that first we'll get the chunk, right? And as I told you in recursive chunking, nothing should be greater than a certain chunk size, which is 1000 in this case. So we'll check if it is greater than 1000. If it is less than 1000, then that becomes a full chunk. That's fine. If it's greater than 1000, we'll first chunk by double new lines. The second recursion is single new line, and the final recursion is sentence. So if you go to the recursive thing which we saw, in this example, I had a section, paragraph, and sentence, right? In the code file, which I'm just showing all of you, in the code file, we have three sections. In the code file, we have double new line, we have single new line, and we have sentence. These are the three sections. So first we'll do chunking at this level. If the number of characters are greater than 500, we do chunking at this second level. If it's still greater than 500, we do sentence level chunking. So that's where you will see three sections. Chunking at this double line, that's the top level chunking. Then the second recursion is splitting by single new line. Final recursion is splitting by sentences. So you can run this now and again run. The number of recursive chunks are 2434. So definitely lesser than semantic chunking. And here you will see the different chunks. The number of characters are 700, 780, 800. They will definitely be less than 1000 because that's the maximum chunk size which we have defined. Oh, yeah. So actually, Amit, this is a completely different notebook because the LLM RAG notebook which we started out with, that is a different notebook. We have covered only until this part in that notebook. Tomorrow we will continue from this. But this LLM chunking strategies is a new notebook which I think someone has shared in the chat again. Okay, so now we have done recursive chunking. Now I want to do structure-based chunking, and here we are going to do a small trick. So, and this is again comes to the engineer's decision, right? I have looked at these chapters, and let me ask you this question. I want to do a simple structural chunking right now, where I want every one chapter to be one chunk. Because at the start, we asked ChatGPT how much total tokens was there, right? It's around 1.4 million. And if there are 20 chapters, each chapter will be maybe 20,000, 30,000 tokens. So I want one chapter to be one chunk. Now, if you are given this problem that you want one chapter to be one chunk, how will you do this? You have right now, let me go to the table of contents. Yeah, this is the table of content, right? And I want each chapter here, let's say this chapter, I want the whole chapter to be one chunk. So this whole chapter is one chunk. Then food quality is the second chapter is the second chunk. That seems the best thing to do over here, right? Because anyways, each chapter is very small. So why not have one chapter as one chunk? So this lifestyles and nutrition will be one chunk. Then achieving a healthy diet will be one chunk. How will you do this? How will you tell the PDF when the chapter starts? Font format. Use chapter marker headings. OCR. So let's say we don't want to use OCR, Samrat, for this. And even when you use OCR, how will you do it? So one suggestion which many people have mentioned is exploit the uh, this font style, because only the title will have this font. That way you'll know at what page you are. Or someone has mentioned go through the table of contents, but that will be a bit tricky. Use page number information from index. That's also very interesting. Split PDF in pages. We are already splitting PDF in pages, right? But how will you split according to chapters? We don't want one page to be one chunk. We want one entire chapter to be one chunk. Average pages each chapter has, but then again, you will lose out some information. So I'm going to do a simple trick. What I'm going to do is that wherever a new chapter starts, I've seen that there is this common text which appears everywhere. University of Hawaii and Human Nutrition Program. Let's see if it appears at all chapters, right? Yeah, see, whenever a new chapter starts, this text is always available. You will see that in all the chapters, whenever a new chapter starts, this is always there. So what I'm going to do, this is called as regex methods. I'm just going to use regex is simple string matching. I'm simply going to match wherever I see that string. Wherever I see this string, I'm going to look at the text which is before that string, and I'm going to start the chunk from that place. That's it. This trick would work here, but how to go about it in general? That is the thing, right, which I'm teaching you here. There is no general when it comes to industrial problems, because one industry might have data stored in a certain manner, another industry might have data stored in another certain manner. You need to develop the capability of smartly using your intuition to know what thing to do at what time. In the class, what I can do is I can teach you 5 chunking strategies, but in the actual problem, you might get a document where you might need to use tricks like this, which are specific to that document. And we have used so many such tricks in all of our industrial problems. There is usually some special thing about each data. For example, some data might have a tabular structure on a certain page. Some data might have a concluding point section at the end of every chapter. You can exploit chapter related specific information based on that piece of text, and all the other pieces of information other students in the chat gave, right? First, going to the table of contents, getting the page number from there, that is a definitely doable trick. Second is, of course, font style, that you get the font style based on the title, and you can do it. In some PDF documents, sections are digitally marked as sections. Those sections, Docling can itself extract as sections and subsections. But if it's an OCR type of a thing where nothing is digitally marked as a section or subsection, you might need to do tricks such as these. Yeah, right. So now what we are doing is that we are we are at this structural chunking, and you'll see we are doing a simple regex here. Import RE, which is regular expression or regex, and we are going to search for wherever this University of Hawaii appears. And what we are going to do, oh, I think my audio got cut again. Yeah, so here what we are doing is that we are doing a simple regex search wherever this text University of Hawaii appears really. And then what we are saying is that we are going to take the text before the University of Hawaii header line, which is going to be our title, which is going to be this at the moment. And then we are going to make a full chunk from that. That's it. So this code seems a bit long, but the simple logic which we are implementing is essentially wherever this text comes, right, that is going to be my start of the chunk. And wherever this text comes again, that is going to be my end of the previous chunk and start of the new chunk. If the context size of the nutrition PDF was huge, how was the chat GPT able to identify the context size with exact numbers? Ideally, it shouldn't have even processed. That's a good question, right? And I think, let's see, the number of characters here are 1485282. So I think it's not an exact answer here. It may be based on an approximation, but I doubt that these are actually correct results. Okay, so now what we can do is that let's run this and let us see the number of chunks. So the number of chunks is 171 because those are the number of chapters which we have, and we can inspect every chunk to see whether what we have done correctly or not. So see here, this is chapter 42, which is, let's say, lifestyles and nutrition. Let's see whether that is correct or not. So go to the table of contents. Go to the table of contents. Where is lifestyle and nutrition? Lifestyles and nutrition, I think. Yeah. So see this. This is lifestyles and nutrition. And when I click on this, yeah, see, this is our first chunk. In addition to nutrition, health is affected by genetics, etc. In addition to nutrition, health is affected by genetics, the environment. So now we have retrieved, this is one chunk, which is that chapter. Then let's see whether this is correct or not. Another chunk seems to be a chapter named phytochemicals. Yeah, so this is also a chapter which starts with phytochemicals are chemicals in plants that may provide some health benefit. Phytochemicals are chemicals in plants that may provide some health benefit, right? So in fact, every single chunk, if you see, is one chapter, which we have now very smartly deconstructed over here. And one thing you'll immediately notice is that the number of tokens in each chapter are different because, of course, the number of pages in each chapter are different. So, and the number of chunks are also much lesser. We only have 171 chunks here, but the size variance across chunks is very large. But you see, with a simple trick which we did here, we were able to do structure-based chunking. This thing which I did here, when you are faced with an industry problem, this is exactly what you will need to do for your given problem. Because your data might be different. Your trick, the trick which you implemented right now is not scalable. Your trick might be something different. Because you're looking at the start and end of university, wouldn't you be missing the topic headers? Yeah, we will be missing. We can add those manually later. What about images and tables in this PDF? Are we handling them? So images and tables are, there are no tables. There are some tables in this PDF, but they are treated as images here. And we are only dealing with text for now. I'll show you tomorrow how to deal with multimodal data and how to store those as embeddings. This code will not work for other PDFs. How about making things general with multiple PDFs? So with multiple PDFs, right, what you will need to do, Samrat, is only, like, let's say, for example, if you have a PDF, right, a tool like Docling will automatically generate sections and subsections. It will identify sections and subsections within that PDF. So then you don't need something as complex as what I did right now. The reason I showed you this code is because you can also do custom structural chunks, which is very much needed in industry. If you want to do a simple PDF project, Docling can even identify tables, it can identify headings, sections, subsections, etc. We are only outputting some tokens. Yeah, so we are randomly outputting some tokens from each chunk. The one chunk is full chapter in this case. So I'm just outputting some random the start information from each chunk. The last thing which we have to do is LLM based chunking. Now this is where I think that if you scroll down into the Google Colab notebook, which I have shared with all of you, yeah, the OpenAI API key, this you will need to enter from your side. Because here what we are going to do is that we are going to ask an LLM to create chunk boundaries for us. So if you check the prompt, we are going to tell the LLM to analyze the following text and identify the best point to split it between two semantically coherent parts. That's it. So here humans are kind of offloading everything to the LLM. And we are hoping the LLM takes care of this. So I ran this right now. And this portion will take some time because we are processing through 1208 pages, right? So this portion is going to take a bit of time. It is going to take a long time actually. So I'll pause this running for now. It might take around, I think, 9 to 10 minutes. Let's see. Meanwhile, if there are any questions in the chat, we should remove the University of Hawaii. That's a good point. We should remove this for sure. And we should take the title into account. But those things can be done manually. There is a question, I think, about how do we deal with multiple documents. So there is also something called cross-document chunking, where you can, the simplest thing to do is that if you have multiple documents related to a topic, just add all of that into the knowledge base and follow the same pipeline which we are doing right now for multiple documents. Do we have open source LLMs for this? We do have open source LLMs for this. In fact, tomorrow, what we are going to do is that if you look at the first code pipeline which I shared with you, this code pipeline, we are going to run this end to end tomorrow, and here we are going to use an open source LLM. So we are going to run it on our own GPU. Overall, I want to show you closed source as well as open source LLM. For closed source LLM, what we are doing right now, the OpenAI approach is fine. But for open source LLM, things can get slightly more difficult. But a local RAG pipeline, I hope all of you can understand why a local RAG pipeline will be useful. Because some companies don't want their data to be sent privately. They want their data stored privately. They don't want their data to be sent to another API call, let's say. Does LLM chunking help reconcile if any logical differences when multiple sources are used? No, not really. Because what LLM chunking does is that if you do semantic chunking, then some coherency is there across different chunks. But structural chunking, fixed size chunking, they don't take into account semantic context at all. Just a quick note, yeah, the API file, we can also store it in the secret keys actually, which is a much better practice to do. But for the sake of simplicity, I have just added it over here. How do we mask PIs here? Yeah, that's, again, that would come in the named entity recognition part, right? So let's say, for example, if you have a document, so by PII, I think you mean personal identification information, right? If there are documents where you need to mask PIIs. It's a good question. So, and someone had even asked a named entity recognition question at the start of this lecture. The way to do named entity recognition is again to make structures in the document in a very clever format. So what if you can use another LLM to detect places where PIIs are observed and then store that and then only extract information relevant to that. One tool which can do exactly this is called as lang extract. How many of you are aware of this tool? This tool was recently released by Google. It does exactly the same thing what you're asking. It looks for specific things in a piece of text and extracts only that information using large language models. We are right now testing this on an industrial application actually. It has some issues, but it's an amazing tool where basically what you can do is that you can extract structured information from even unstructured text documents. And you use an LLM to do this. So if you want PII or personal identification information, you can just pass that as input source to lang extract, and then you retrieve only that relevant information. And then you can mask it very easily. Once you retrieve that information, masking is not going to take that much time. If you are dealing with legal files, not just legal files, if for any let's say if you want to make an Aadhaar application, right? If you want to make an Aadhaar rack system, you need to know important information related to a person, which can be their name, date of birth, address, and that can be scattered throughout the document. How do you retrieve only that portion which matters? There have been natural language processing models developed specifically for named entity recognition. You can use those for sure, but now you can even use generative models. People who have been attending from the live lectures from day one now know the difference between there is a trade-off when you use generative models, right? You cannot randomly use it for all applications. In this LLM evolutionary tree, this gray side is the LLM part, the generative model part, usually more expensive. But this red tree are representative models, and they can even do many more tasks uh, in a much cheaper price, in much lesser number of parameters. So always keep this trade-off in mind. Don't randomly use a language model. Let's say for named entity recognition, you can even do a simple. So for example, yeah, I'm sure Hugging Face has huge number of models to do NER, right? Like this is the bird-based named entity recognition, fully open source, has around 2 million downloads per month, looks to be highly robust. Which is the best tool to extract information from handwritten purchase orders. So I cannot recommend directly like that, Amit, because as we have discussed so far, it's the engineer's choice, right? But hopefully I've given you enough tools to make that choice yourself now. Because if the handwritten purchase order is there, of course, you will need to use an OCR tool. But if you want to use, if it's a complex data, you can use Docling. But again, we'll need to look at data. You can even use lang extract, which I just showed you right now. Okay, so let's see. How many of you are running this, by the way, this LLM based chunking? And how many of you are not running this? Can you just small brief meaning of named? Oh, NER is actually named entity recognition. So named entity recognition is as named entity can be a name of a person, can be address of a person. Named entities, if you need to identify from a document, that's called named entity recognition. So it's like if you want to extract specific entities, like by entities, it can be personal identity information, anything else. So, okay, so I can see that many people have finished running this actually. I'm also almost done over here, but you can see that in this document, whenever I mention about LLM based chunking, I mentioned the trade-off of computational size, right? And expense, computational expense. Already you must be observing that all previous chunking methods ran in a fraction of a second. But the moment we used a generative model with the trillions of parameters, it takes huge amount of time. And right now, since we are doing it on a Google Colab, it's fine. But for an industrial project, this time can be extremely prohibitive to the client in terms of cost. Remember, every call which we are making is charged. So now we have 2360 chunks over here, right? And we can even print out these different chunks, how they look like, etc. Again, since it's LLM-based chunking, we are at the mercy of the language model to decide where to make splits. But this seems to be much better than semantic chunking. Why? Because in semantic chunking, we used a very simple model. Remember, we used a model which has around 1000 times lesser parameters or 10 raised to 5 times lesser parameters than the GPT model which we used for LLM based chunking. So of course, since we used a larger model, it has to do a better job. So here it has converted this into 2360 chunks, which is much better than the 12,000 chunks which we saw in the case of semantic chunking. The LLM evolutionary tree, someone has asked, right? So if you can just search, there is a GitHub repository. It was being maintained practically, it was being maintained until a certain amount of time. That's where you will have the graph. Anyway, so now the 5 chunking strategies are done. And here is where we can actually do the evaluation of these chunking strategies. This is going to be a simple statistical evaluation, but you can actually see the average chunk size. And here I'm looking at the number of words in a chunk. So this is just average chunk size is 62 words. Number of chunks is 3321 and the size variance across the chunks. So just take a look at the different things here. First thing which you clearly observe is that the number of chunks in semantic chunking are huge. They're much higher compared to all the other types. And the number of chunks in structural chunking is much lesser because we are taking each page as one chunk. Sorry, each chapter as one chunk, if you remember. So every chapter is one chunk. That's why there are only 171 chunks. But in semantic chunking, we used a transformer model, which is the open source from Hugging Face. So it made very granular chunks. Then take a look at size variance. Fixed chunking is extremely compact. Semantic chunking is also quite compact, it seems. Because why semantic chunking compact? Because there is no one stretch of paragraph where semantics is apparently retained. But structure-based chunking, there is huge size variance because there is a lot of difference between the chapter page length. And LLM-based chunking, if you see, it always provides a moderate performance. It provides balanced results, which might be indicative that this is a good thing to go ahead with, but again, it's extremely expensive. So in this particular case, just let's say you are doing this problem for a nutritional chatbot. We have not implemented the RAG pipeline, but already we know which methods not to use, right? We should probably not use LLM based method because it takes a lot of time. We should probably not use fixed chunking because it's not the ideal thing to do is break according to chapters. And semantic chunking is also not very good because the number of chunks which are being given to us are very large. So we might do a structural chunking or we might do fixed chunking with, let's say, more number of sentences grouped together, etc. These are the kind of insights on chunking evaluation which you can get at this stage. Yeah, we should definitely benchmark time. Recursive chunking again is a good trade-off between all the things if you check, and that's always the case. Recursive chunking time is also good, size variance is less, number of chunks are moderate, average chunk size is also moderate. Because as I said, it's the best of both worlds, right? It does not have too large of chunk sizes, and at the same time, it maintains the structure. Finally, you can visualize these things which we just saw. For the chunk size, structure-based chunking, of course, has the largest chunk size, and semantic chunking has the smallest. Number of chunks, it becomes reverse over here. Semantic chunking has the largest number of chunks, structure-based chunking has the smallest. Recursive and LLM are moderate. And chunk size variance for structure-based chunking, it's way higher than the rest. You can even do a box plot of the sizes, right? So for structure, you can see the variance in the chunk size. So final takeaway here is that structure-based chunking produces the largest chunk, fewer in number, but with very high variance. It is best for capturing entire sections, less balanced for downstream models because of the size variance. Semantic chunking produces very small chunks and the highest number of chunks. It preserves fine-grained context, but it risks over-fragmentation, which means chunk size is too small that we are really not capturing any meaningful information in one chunk. Fixed size chunking produces consistent moderate chunks with low variance, but it ignores semantic boundaries. Recursive chunking, as always, recursive and LLM chunking are balanced approaches. But I actually did one mistake here. I should have benchmarked time also. If I would have benchmarked time, LLM would definitely be out of the picture. It's 2 orders of magnitude slower than other chunking methods actually. Yeah, so this brings us to the end of day 1 of this workshop, where we actually covered. Let me do a quick summary of what all we have covered. I again want to thank all of you for staying till the end. I had originally planned it to be a 1.5 hour session, but it actually became a 3.5 hour session. So we have covered file parsing and we have covered chunking so far. And still we have to cover embeddings, which we'll cover tomorrow. Then we have to cover evaluation. And then I want to show you how to build this production level RAG pipeline. Thanks a lot, everyone, for staying for 3.5 hours. I think many of you actually stayed. If you like today's lecture, definitely attend tomorrow, because tomorrow we'll directly take off from where we left. We'll directly, so this chunking thing has finished. Now we'll start with embedding. So we have embedding remaining, we have retrieval remaining, then we have generation remaining, and finally we have the production level system remaining. Thanks everyone. Then I look forward to seeing you tomorrow. Bye.